From a mind that defied conventional aviation comes a foundational understanding of flight. Today, we delve into The Secret of Flight, a complete set of lessons from the legendary German aeronautical engineer Alexander Lippisch. Restored and now in vibrant color, this is more than just a historical document. It's a deep dive into the very principles that govern how aircraft take to the skies. Lippisch, a pioneer in delta wing and tailless aircraft, brought a truly radical vision to aeronautics. Prepare to unlock the timeless wisdom from a true master of the air.
We call this series of programs The Secret of Flight. And we could have probably called it also the mystery story of the streamline to be up to date. And you might wonder, what's all the secret about? Can't you buy yourself an airliner ticket, drive out to the airport, board the plane, take your seat, fasten your seatbelt, and with roaring engines, off you go. After the plane has climbed to the proper altitude, there comes the voice of the captain through the loudspeakers telling you that you are flying at 20,000 feet altitude with 320 miles per hour, and that the weather is fair ahead and you will have a pleasant flight. So you make yourself comfortable in your seat, read your favorite magazine, light a cigarette, and probably look out through the window to the wide plains, to the little farms and towns. And you might also have a glimpse through your window of the wing and a view of the engine against some beautiful cloud formations which you see at the far horizon. Well, there is certainly no secret anymore that this slender wing and these four powerful engines support an aircraft of more than 100,000 pounds, which connect towns, countries, and even continents with the fastest means of transportation. What was once a dream of the pioneers of aviation 50 years ago became a reality through a scientific and technical development of unforeseen rapidity. But while you are looking out there, something is still mysterious to you. Where is the road on which you travel? Where is this element which supports your flight with such invisible power? Well, you feel the forces of the air on the aircraft, and the pilot can tell you how these forces react if he changes his controls. And you probably could even ask a scientist, an aerodynamicist, and he will give you long mathematical explanations of the laws of fluid motion and how you can figure out these forces, at least approximately. Well, this would not satisfy your search for better understanding. If you only could see what happens, if you could make this process visible, you would at once conceive basically what's going on. And it was one of my pet projects to make an instrument where we could visualize basic flow processes. You know, a picture is better than 10,000 words. And if we can make nature to show this flow process visually, then we would have a mean of simple conception, and we would not need all this complicated mathematical explanation. And therefore, I built this smoke tunnel. And there it is, the view field of our test section. Now, the white lines which you see there are really streamlined. You might think that we have put some threads, white threads in there, but this is not so. I can prove it to you. When I shut the tunnel off and the motion slows down, then at once you see that this is really a smoke pattern. And it really gets a beautiful pattern as you see it now. If I start it again, there are our straight streamline. Now, if we have something in the tunnel, some model, we would see the flow pattern which is formed around the model. Watch this. There it is. The streamlines now don't, as you see, bounce just against the plate. Oh no, they go smoothly over it, but at the corner of the plate, they stall away and don't come back to their original position in this tunnel. Oh no, there is behind this plate a large area of dead air. And when you would think, you would stand there, you might feel only the local turbulence and a little flow from the backside. But it is especially interesting to see this transition while this plate flips up. And therefore we have made a slow motion picture of this action. First we see the normal view field as you saw it out there. And now the plate comes up. And watch this. It forms first a small circular vortex behind the plate which floats away. And then the whole large area of dead air in the lee side of the plate begins to form. You actually see a little oscillation on the plate itself because it's sprung up by a spring which makes some damped oscillations until it gets into this steady position. You see on the border of the dead air and the flow itself, you see what we call a discontinuity line, where a mixture happens between the outer air and the flow in the lee zone of the obstacle. You know, to see what's really on such a flow picture, you have to get acquainted with it, and it might be quite new to you. Therefore, we want to show you this flip-up plate once more in normal speed, as it is here. Now watch it again. There we go. There you see again this nice pattern of flow lines which go over this obstacle. And observe the reverse flow which you have behind the plate. It's really something which you might often experience in nature itself, where the wind suddenly comes from the other side due to such a reverse flow in a dead air zone. Now we want to go again and show it in slow motion. So straight parallel flow line, and pretty soon you will see here how this plate comes up and how this circular vortex is formed first, and then floats away and the large dead air zone behind this obstruction is formed. In the boundary between the lee dead air and the outer flow, you have small vortices, which you can see here, which always protrude into the dead air zone and form also such a wavy front between the flow, outer flow, and the calm zone behind the obstruction. On the other hand, one thing is interesting here, that the flow lines of the undisturbed flow go much higher than the height of the obstruction is. So if you stand behind such a thing, you easily can look over it without having any blow in your face. That is the secret of a windshield. While we are preparing the tunnel for another test, let me just briefly explain to you how this instrument works. Now, you might first ask, what is a wind tunnel? Well, a wind tunnel is an instrument to measure the forces of air on models' airplane parts. And we might even look into the Webster to find the right definition of a wind tunnel. Let me just read it to you. I think it's there. There it is. A wind tunnel. A tunnel-like passage through which air is blown at a known velocity to determine the action of wind pressure on structures, airplanes, etc., that are often in the form of models of reduced dimensions. Well, Webster certainly knows it. Now, this wind tunnel is a special one. And you can see here the top view of this whole installation. It consists mainly of three major sections: the intake section, the test section, and the blower section. At the intake section, we have a large nozzle and go into a silencer chamber where we have fine mesh wire screens in it to break up the large disturbances which might come from the outer, and also to damp out any noises which would come from the outer and disturb our flow. After we have made with these fine screens out of the air which comes in a micro-turbulent air broken up in all little fine bubbles, we contract it through a nozzle, and due to this contraction we get all the turbulence out and get a complete, smooth, steady flow into the test field. Then we blow the air from the test field into the blower section where we have a little settling chamber, take it out with the blower and through a smokestack, blow it out into our system. We control the models from a control panel, and our smoke is introduced at the nozzle where we have a smoke strut, a streamline-shaped strut where very fine tubes come out, and through each tube we blow the smoke into this accelerated flow. You might be interested to see such a smoke generator, which we have here put up for you so that I can demonstrate it to you. This instrument actually was designed by British scientists, and it works in this way. We have here an oil container, and through a communicating system, the oil goes into this tube where we have a heating wire on it, heat it up, evaporate the oil, which then goes into this chamber through a very fine nozzle. This jet stream of this oil vapor which comes out there is then cooled down by air, fresh air, which is blown through a pressure system into it. Due to that sudden cooling and expansion, the oil vapor forms a fine mist, which comes then out here as this smoke, a very fine smoke which does not clog up your lines. Now let's have a look around the tunnel. Here you look into the intake, the large nozzle which goes into the silencer chamber. The structure itself is mainly a wooden structure. Here we have the silencer chamber where we have the screens in. They are put in here and can be exchanged so that we can clean them, because to have clean screens is very important, otherwise our flow would be disturbed. From there, the flow, as I told you, goes into this nozzle, which is large conversion nozzle of a convergence of 1 to 20. In front here we have the control panel. Now, these three wheels are the model controls, where we can turn with them the models to give them certain motions of the angle itself, of flaps, and things like this. This is a mechanical connection through the back of the tunnel to three concentric tubes where you attach the model in it at the rear glass wall. Here we have the usual switches, the main power, and here are the lights. And from here you control the blower, the speed of the tunnel, and the blower himself. And with this little instrument we can measure how much speed we have through the test section. This tunnel we have built at the Collins Aeronautical Research Laboratory with the help of the Office of Naval Research in Washington. Now we get here to the test section, and let me show how we put a model into it. We open up the front window, supported because it's quite heavy. And here we have the model. You see, that is a kind of a bayonet attachment where we put it in, so, and then close the tunnel again. And through these controls, I can now move the model from here up and down. And now let's turn the smoke on. There we have it. And there is our flow field with the plate parallel to the direction of the flow. So you see practically no disturbance except this small turbulent layer, which is caused by the friction of the air on the surface of the plate. But now watch. When I turn the plate across the flow, first of all, it begins to stall, to break away a little bit. And then, when I turn it on more and more, and finally have it at 90 degrees towards the direction of the stream, we get that violent oscillating motion, a so-called Kármán street. Since Professor Theodor von Kármán was the first who investigated this phenomenon. You might see it even better if I turn the blower down so that the whole field slows down and we see it in a slower motion. See how these vortices are generated from the tips of the plate, always intermittent. See, now the view field fills up with smoke. And when we start again, then we have the transient picture of this flow, which we actually can observe much better if we have a slow motion picture. First, we see a straight wake with dead air extending from the plate backwards. Both sides are the same, but we see at once beginning an oscillation back there at the end of this wake, like on a flag. And this is transmitted slowly against the flow direction towards the plate. And finally, this results in an pulsating intermittent formation of big vortices from the corners of the plate. This we call a Kármán street. Since the well-known aerodynamicist Professor Kármán investigated this for the first time and found that only such an intermittent motion and position of these vortices could exist due to stability conditions. We will come to this later in one of our other programs. Observe here mainly the magnificent pattern of the flow and the speed which you have locally in these vortices, which is quite high, because you must think that this low speed picture makes about a second to a minute. You might think that this generation of these intermittent vortices is mainly caused by the sharp corners on the flat plate. But unfortunately, that is not so. Even a circular cylinder, a rod, would cause such oscillation. And we have put one cylinder into the tunnel, and when we turn the smoke on, then we see that we have the same type of a vortex street behind the circular cylinder. So actually, we have to have another form of body to diminish this disturbance behind such a body. Now my assistants have put in a streamlined body in the wind tunnel, and to explain the shape, the evolution of the shape to you, we have probably to go back to this phenomenon of the vortex street behind the body. Actually, you can observe this quite often in your normal life. For instance, when the wind blows against a wire, this fluctuation excites the wire and makes it to vibrate. So that's what you hear. This wire whistling is nothing than such a, as we call it, Kármán street behind the wire. Or you want to move an oar through the water or a round rod, and you will find that you can't move it straight. It always oscillates due to these vortices which you generate with the oar or with the rod. Now, this is certainly a phenomenon which we don't want to have in airplane design, because it would cause large oscillations and also lots of drag. To get rid of it, what you would do, first of all, you must see that the front part on the front part of the body, the flow was nice and smooth, and your trouble started at the rear. Therefore, you have to do something at the rear, not make the front pointed. Oh no, let it be rounded. But fill out this rear part with a body which is slightly convergent, so that this vortex generation can never start. Here you see a typical streamline shape. And you see no vortex generation anymore. A small disturbance back there, this little blurred part where the air gets turbulent, because we have friction on the walls of the body, which necessarily retards the airflow and makes small disturbances which cause here our smoke lines to blur out. Now, if we turn the body, we can also see it when we have not just a straight flow against it, but the flow comes now under a certain oblique angle. You see that then the disturbance gets somewhat larger. All these things I will explain to you in many of the later lectures, and I wanted to show you today mainly that such a device where we can make the flow visual, where we can see what happens, is a very helpful tool in our aerodynamic research, as we say it, or when you just want to make such flow phenomena understanding to other people. In our last program, we have seen several flow pictures in the smoke tunnel, and I have explained to you how this tunnel works. Today, I want to show you how we can determine the forces which act on a model in a tunnel and the different velocities which are there. Well, the forces which are produced by a flow over a body apparently are forces of the air pressure against such a body. For instance, when an aircraft flies, the lift is produced by pressure forces on the surface of the wing, and this keeps the airplane flying. Have you ever seen an airplane take off? Well, to show you this time when the lift begins to go, we have made a picture of a light plane taking off from a runway of an airport. And there it is. Let's look at it. First, we see the plane rolling on the ground, then it gains speed, and then the pressure forces are so large that they lift the plane from the ground and it flies, supported by the air pressures in the same way as, for instance, a weight would be supported, which is here laying on the table, by the pressure from the material of the table to the weight. It's exactly the same thing. Now, how can we do and see it in this smoke tunnel? We see there only a section of the flow. We see only a cross section. And to explain it to you more specifically, I have here a model of a light plane as we just saw him in our movie picture. And when I now take the swing off and show you the side view of it, then you might be able to compare it with what we have here as a model in the wind tunnel. There we have part of the wing, and we have outlined the fuselage with a thin piece of plexiglass on the rear wall of the tunnel. If I now turn the flow on, and we have our smoke generator going, then we can see the flow over this model, especially over its wing. First, as it took off, it was flat, and then the pilot turned it over and we got more lift, and it lifted from the ground. Now, apparently, we cannot see any pressures. So we can only see the scales, for instance, on a pressure measuring instrument. And in flow, where we have quite low pressure differentials, we use what we call a manometer, a fine pressure gauge, which works in this way. We have a U-tube, and this U-tube is filled with colored water to a certain level. If we now blow into one tube, for instance, through this rubber hose, like this, then you see that the pressure which I exerted here through this hose on the water level is to be read by the difference between these two water levels. Here, for instance, let's see, 2.5 inches of water. Now, what is 2.5 inches of water? Well, we have a wonderful, simple English system of units. And then when we figure this all out, which takes us quite a while, then we find out that 1 inch of water equals 5.2 pounds per square foot. Now, what is pounds per square foot? You probably are not familiar with this type of unit. You usually measure pressures in PSI, as you measure, that means in pounds per square inch, as you measure it, for instance, on the tires of your automobile, where you have about 28 PSI into it. And you measure the same PSIs on a pressure tank, which you probably have in your basement for anything. So what is a PSI when we think of inches of water? Then we find out that 1 PSI equals 27.7 inches of water. So that means when we have here 1 inch of water, or sometimes even less in such pressures which we measure in a flow, then this is extremely small. Let me show how we, for instance, can measure how much flow we have in this flow of a vacuum cleaner. If I put, for instance, this hose direct against it, you see then that this blast gives us about, not quite an inch of water. And with some tricky formulas, we can figure out how much velocity this is. I don't want to annoy you with this. But you must think that these small pressures don't amount to anything when we think of the pressure which we have, for instance, in automobile tires, where we have compression of the air. So if we have a few inches of water, there is practically no compression or expansion of the air. And therefore, the scientist treats such flow as we have it in normal wind tunnels, or as we have it up to 300 miles per hour flight speed as the flow of an incompressible fluid. Now I want to explain to you the correlation between the velocity and the pressure on the surface where we blow the flow over it. There's one important thing to understand. That is that when the velocity at a certain point of our model is larger than the average velocity, the pressure on the surface of this body is lower than the average pressure. And if the velocity is smaller than the average velocity, our pressure is higher than the average pressure in the whole fluid. That means we have to know all the time that if velocity increases, pressure decreases. And if velocity decreases, pressure increases. Very important to know. And to show you this and explain it as good as we can do it in this tunnel, we have put here a so-called multi-manometer. That means a multi-pressure gauge on a certain model in our smoke tunnel. Now let's have light so you can see the model. And if I now blow through the tunnel, then you see that this manometer reads certain pressures along the surface of this body. How we did it? Now, we have fine holes on the surface of the body. These fine holes are connected through rubber hoses, through the model here and out there, back there, on the tubes of this multi-manometer. And the other ones are all connected with the average pressure, which we read in front of this test field where our flow goes in with its mean velocity. We see now, since this is convergent, the velocity must increase. And since the velocity increases, our pressure must decrease. That means we must have kind of suction on the surface. The air must suck away some fluid out of this line. And this makes the water column go up here. So if the water column goes up, we have suction. And where we have the highest velocity, we must have the highest suction or the lowest pressure. That would be on such point like here. Now let's see. This point corresponds to this line. And you see at once this is the highest water column which we read here, where we have the highest velocity through this cross-section. Now if we turn the smoke on and let our smoke generator go, then we can see this flow field. And we see that when the velocity increases, our distance between the flow lines gets smaller and smaller. So if flow lines are very narrow together, we have a high velocity and we have a low pressure. How can we see this velocity business? Now we make a trick, and that is we pulsate the flow. That means we let pulses into the smoke system, and so our smoke comes out in fronts, little puffs. But we can even see it better if we observe it through an optical system. That means we take our high-speed movie camera and make a slow-motion picture of this pulsating flow process. And then we see at once that our velocity in this region is much higher than here. Let's just look at this film. There we are. You see a very interesting thing here. that the velocity increases first in the center of the smoke front and then goes with even velocity through the narrowest part of this channel. We call such a line which goes through there a timeline, because actually this indicates the particles of the air which come all at the same time into the flow and travel through there, and the different shape of this line shows us the time history of the flow. Now, to see another pressure distribution, as we call it, that means the distribution of the pressure over the surface. We have taken out of the tunnel one side of this nozzle, and then we have the flow over a hillside or over a hump, and we can see then how the pressure records now. There we are. I turn the flow on, and you see when we take this out and we have more space, our velocity doesn't go as high as it went when we went through this narrow nozzle. Therefore, the pressure doesn't read as high as it did read before. And we see one other thing. We see that the highest point is now this one. That means here. It reads here the highest velocity. And the velocity here, as it was before the highest, is now smaller and declines since the whole flow begins to slow down to the original cross-section which we have at the rear of the tunnel. Now, if we turn the smoke on, then we can see the flow field itself. Here it is. And we see at once that in this region we have the highest velocity, because there our flow lines are the most pushed together. Here down there we have even a little bit pressure. We see that because this one records a little lower than the average pressure. Now, if we do the same thing again with pulsating smoke, then we can see also the velocity field. You see, when we have normal velocity, that goes too fast. So I have to cut the speed out and slow the tunnel down, and then we can see it by eye. But again, better we see it in a slow motion picture, which we have here. There it is. There we see that the velocity at the lower part of the tunnel decreases considerably before it hits the bump, and then is suddenly accelerated. But the whole front bends over. Now, we have another little trick, because we want to demonstrate to you the flow and the pressure distribution due to this flow over a wing section or type of a wing section. Now we had this hump. When you think, the upper surface of this hump had almost the same shape as the upper surface of a wing, slightly rounded. So we take our hump and lift it up into the center of the view field. And then we have a large wing section-like model in the tunnel. And we can see now the pressure recordings on the upper surface of this wing section. When I turn the blower on, then you see here in this multi-manometer or pressure gauge, you see that we have again suction, lower pressure on the upper surface due to the higher velocity which we have up here. Interesting to see, first of all, the first one, which is this one, records a little lower than the average. That means here we have actually some pressure on the surface. from there on, the speed increases and the pressure goes down and we have suction, and this suction on the surface sucks our water lines up, and this shows the pressure distribution over this surface of a wing section. If we now have smoke lines, then we can see the flow picture. And you see very clear that the velocity here is much higher than there. See how narrow the lines are here and how wide they are in this range. On the other hand, you see that here the flow somewhere goes to a point on the surface. And this we call the stagnation point, where the airflow stagnates. It is stopped completely and would record, if we would have here a pressure, the stagnation pressure, which is a higher pressure than the average pressure of the flow. Now, if we take again our method of pulsating the smoke, then we can see this velocity distribution. And to make it visible to you in this flow field, I stop the blower so that the tunnel slows down and we see a little bit at least these smoke fronts going over the wing section. Better we see it in a slow motion picture, which we have here. And there we see very clearly that the velocity on the upper surface of the wing section is higher than below, because we have a very distinct shift of the two parts of the smoke front which goes over the wing section. This shift of the timeline of the smoke front indicates lift on the wing section. And by some tricky mathematical calculation I didn't want to explain to you here because you would sleep with it, you can calculate the lift you have on such a section from the shift which you see here. Now, you have seen this phase shift of the big wing section in our tunnel. And some of you might say, all right, that's due to the fact that this thing is so large and the tunnel is quite small. And therefore we have blocked some area above and the velocity must be higher. And you have cheated me. And I will tell you, I did not cheat you at all. And I can prove it. Because we put now a small model in this tunnel, like this here. And when we do the same thing, we pulsate the smoke again, you will see that again the upper flow is much faster, and behind the wing section, still far away behind it, you can see very clearly that you have this phase shift in the timelines. Now let's first look at this thing with the normal smoke on. There is the flow, and now we get the smoke generator going, and there's our flow picture. You see, this is an angle of attack, almost zero. We measure it from the lower surface. And what you see here also, very interesting, is a little stagnation point. This is a stagnation point of this section in this angle of attack range. And if we pulsate the smoke now, then you see this velocity field. Well, you can't see much here. But if we look at the high-speed movie or the slow motion picture or at the smoke lines here, then we might detect this shift. Let's look at this here. There we have the same condition as we have put it here in the slow motion picture. And you see again very clearly this shift in the timelines. the same way as we saw it on the big wing section. Now, if we see this with a higher angle of attack, then the lift is larger, and therefore our shift in the timelines must also be larger. Now let's go back to our smoke lines in the smoke tunnel. We can see other things too, especially if I change the angle of attack. See, when I change the angle of attack, then you see that the lines on down here get wider and wider. We get more pressure underneath, and the lines up here get narrower together, so we have more speed, especially in this region. We increase the lift. Another thing we see is that behind the section, we get a larger area of turbulence, of air which doesn't have anymore the main velocity of the flow because it's blocked off and also slowed down by the flow on the surface. If we go much higher, then this blocking is so strong that the whole thing stalls away, as you see it here. And then we have no lift. It's a very difficult condition and very dangerous for somebody who wants to fly with an airplane. He has to learn that if you have too much angle of attack, your flow stalls, as we say it, and breaks away from the upper surface where you have most lift, and your airplane falls down, and you have severe accidents if you stall an aircraft. Now I think we have understood how we can analyze such a flow picture, and we got a little idea why an airplane flies. In our next program, we want to give you a little story of the past. You see, this flow and basic law of fluid motion was well known for quite a while before any activity were on to try to solve the problem of the flying machine. And the first, I think, whoever at least made a model of a flying machine was a Frenchman named Alphonse Pénaud. He made a small model of an airplane with a propeller on it and had a rubber motor on it and flew it in 1870 before some of the members of the Academy of Science of France. In the Smithsonian Institute in Washington, there is a replica of this model, and I have here another one which I can fly. Unfortunately, this area which we have here is a little bit too small to do this. And so we made a little film in the outside where I can show you how this Pénaud model, which is originated in 1870, that means it is now 76 years old, how it flies. From there, we will go through the up and downs of the first development of the flying machine, and we will see how the invention finally was achieved by the brothers Wright of this country. This is a model of the first airplane who ever flew. A model of the Wright brothers airplane of the year 1903. This historical event took place at Kitty Hawk in the dunes of North Carolina on the Atlantic coast. It was December 17, and the Wright brothers, there were two of them, Wilbur and Orville Wright, they made at this day, at this morning, 4 successive flights with this machine. The first one, the first flight, lasted 12 seconds. This is the first takeoff at this first flight under the direction of Orville Wright. And the last flight on this day covered a distance of 852 feet and lasted 59 seconds. They were all on a horizontal course, all the flights, and the wind they flew against it was a gale of 24 miles per hour. So that if you compute this and think that they would have flown the same thing in still air, then you come out that the last flight covered about a distance of 3,000 feet and was made with a speed against air of 34 miles per hour. Now, the question is, how did they achieve this magnificent performance at a time where practically nobody else could ever match such success? Well, if you go back and see what was there on aviation and on knowledge about aeronautics before the Wright brothers. Well, we know, for instance, that in 1870, this Frenchman, Alphonse Pénaud, showed this little powered model of an airplane which contains mainly all the features. It has a wing, it has certain control surfaces, has a little motor, and has a propeller, and is driven by the propeller through the air. And on the other hand, there were several people who began to test models, and there was one, the engineer Otto Lilienthal, who from tests with models, he concluded that it would be the best thing to fly a man-carrying glider and test the results of his measurements with certain wing-shaped surfaces, cambered surfaces. You know, a camber is a curvature of the wing, so it's hollow underneath and round above. And he tested this with gliders and showed that in this way you could get a certain amount of experience in flight, even if you did not have an engine which would propel this airplane in a horizontal course. Now, from the knowledge of Lilienthal, others tried to fly manned gliders. And among them, there was the American engineer Octave Chanute, of whom you see here the picture, who actually contributed several new ideas to the construction and design of such gliders. His main contribution is, in my opinion, the structural design of a biplane. The two superimposed surfaces connected with struts and braced out with wires. This was conceived by Chanute because he was a structural engineer. He built several bridges and designed all kinds of appliances for railroads. And in this way, he knew how to build a light and strong framework. All this was known. And when the Wright brothers began with their interest on aeronautics, which was in the years of about 1897-98, they discussed these things and they drew exactly the right conclusion of it. That means they found out that All this gliding with what we call today a hang glider, that means with a glider where the man hangs in it and controls the motions of the glider by shifting his own weight, would not be good enough to control a larger machine. And they invented at once a control system which now made it possible that the man was fixed in a certain position and moved certain levers, and with these levers he could move the surfaces. He could, for instance, warp the wings. This was the first model they ever tested as a kite. You know, they could warp the wings like this. They could shift the wings forward and backward, and all this with certain mechanical helps, and in this way could be able to control larger machines. After they had conceived this, in 1899, they began to test gliders of their system, and to be able to do this gliding with at a spot where they had good conditions, that means wind and free space. They found this spot in Kitty Hawk at the coast of North Carolina. Now, they, through these years, 1900, 1901, and 1902, they tested several successive glider types and improved it so much that in 1902 they had a glider which performed exactly as they thought it should be. It was completely controllable, very stable, had a large wingspan, much larger than anybody else had ever tested, and they flew in winds where nobody with a hang glider would ever dare to fly in it. With this system developed, they were able to go on and try to build a powered machine. Now, to build a powered machine at this time, it was necessary, first of all, to have an engine. And since nobody could build them an engine, they built it themselves. And they built an engine better than anybody else could do it. A 12 horsepower engine which had a weight of 150 pounds. And they used exactly the system of their 1902 glider, but they had to make their powered machine, as you see here, this is the same scale, larger, because the weight was larger and the machine with the operator would weigh 750 pounds. That means they tried to fly with a power loading of 62 pounds per the horsepower, which never in later years was ever tested. And they tried to fly this machine against such a storm, because, you know, 24 miles per hour on the coast with a December storm which was there is not only a strong wind, but it contains lots of gusts, and you must have a machine which is fully controllable, otherwise you wouldn't be able to fly in such weather. Now, they took off this machine not from wheels as it is done today, but they built themselves a monorail, as you see it here in this picture. This is the rail from which they took off, and they placed the machine on a little trolley which runs along the rails, and they hooked the machine on before they took off. Then they started the engines, and after they were run in, they unhooked the machine, and it moved by the thrust of the propellers against the wind, and after about 40 feet of running on the rail itself, he lifted the machine up in the air and flew against this strong wind, which was at this time, 24 miles per hour. So that actually the machine over the ground had only a speed of 10 miles per hour. Now, these first flights, which showed that it was possible to fly a powered machine with this low horsepower and to control it in strong winds, was the beginning of the further tests of the Wright brothers. See, after they had performed this in the December of 1903, they transferred their experimental work to a place which was near their hometown in Dayton, Ohio. And there they operated improved aircraft in the years 1904 and 1905. And towards the end of the year 1905, they actually had solved the flight problem most completely, since they were able to circle their fields many times and fly times of, well, until the fuel ran out or until the water supply in their radiator ran out, actually about, well, 40 minutes or so. That means it proved completely that they were able to control their machine very efficiently and to fly around as they wanted to do it. So these years are the beginning of aviation, and the work which the Wright brothers did necessarily initiated several other people to try to build also flying machines. As you know, when one man has shown that it is possible, then there is much more confidence to do it yourself and more confidence on others that they would be able, if they would build a good engine, to fly with such a machine. See, the Wright brothers themselves now did not only experiment and build and design this first flying machine, but they also made very excessive tests in a small wind tunnel which they built in their shop in Dayton. Actually, these tests are the first wind tunnel tests, practical wind tunnel tests on wing surfaces, on different shapes of wing surfaces, on different shapes of their cross sections. That means wing sections and all this. And they derived from these experiments a very keen knowledge of the design of such aircraft. On the other hand, see, when they wanted to build their powered machine, there was nobody who could ever make them, for instance, a propeller. Nobody knew anything about a propeller for an aircraft. So they not only had to build a propeller or to design it, but they had to make a propeller theory and to find out in which way a most efficient propeller had to be shaped. And they solved this problem in a very complete way and actually put two propellers at the rear of their surfaces, two very large propellers, so that they would have a very good efficiency. And by gearing them to the engine with a bicycle chain and crossing one of the chains, you see, the one of the chains is crossed, they had counter rotation on the propellers so that they would eliminate the torque of the engine completely. All these features on the Wright machine show that they had a very extended knowledge of designing an efficient aircraft, much more than anybody else had at this time. Now, after having solved the problem, well, they went to negotiate with different governments whether they would be interested to buy their invention. Well, what they found out was this, that nobody believed that they could ever do it. So finally, it came out that they had to show it. They didn't want to show it because they thought, well, when we show it, then somebody else sees it, and then we have all the trouble that they imitate what we have done. But nevertheless, in the years 1906 and 1907, all their negotiations didn't lead to anything, so that finally, in 1908, they had to go and demonstrate the machine. And now, to demonstrate it in this country, to the government and to the army single corps, and on the other hand, to show it in Europe, they had to separate. And WWII went over to Europe, to France, and there to Le Mans, to demonstrate flights there, while Albright went to Fort Myer near Washington to show the flying machine, which was on a contract with the single corps of the army. We have from this time a few films of these early flights. Now, when you see these films, you must be aware that the speed of the films at this time was not what we have today in a modern camera, because, well, the films were not very sensitive. So what you see goes much faster, actually, than as it was done. The airspeed of taking the film was probably 12 or 16 frames per second, and you see it today with 24 frames per second. So therefore, don't bother that they fly so fast and that people move like in a Charlie Chaplin film. This is only due to these old films. But you see there, first of all, their device to take off. Now, see, they didn't want to take off from wheels because they found out they needed too much power. They didn't have that. So they built themselves a device which is a launching device to take off again from rails. And they had a derrick tower with a big weight on it, and this was then guided through a long rope on their track, which was here, and pulled now the machine which was standing on this trolley. This would be their machine. So, and then after they run the engines, they unhooked it and took off with this launching device. In some of the pictures, you see this, and you see how they pull this big weight, I think it is 1,200 pounds, up with several men. And I remember very well myself, I have seen Albright flying in Berlin. When we waited for a flight, the first thing that we knew we were near to something like this was when these men came and pulled this big weight up. Now you see it in the film, and let's watch this. Now, to show you some of the most successful airplanes from the early days of aviation, besides of the airplane of the Wright brothers, we have here some very beautiful models of these airplanes. And let's look first of the most successful competitor with the Wright brothers. This is an airplane from Glenn Curtiss. He worked together with Herring and Graham Bell. This machine actually represents his airplane from the years 1909. It's called the Gold Bug. It's propelled by a 4-cylinder, 35 horsepower engine, a design of Curtiss himself. It is also known as the so-called Albany Flyer, because with this machine, Curtiss flew from Albany to New York and won several prizes, among them the prizes from the Scientific American, and also competed very successful in aeroplane meets at Reims in France. You see, this machine contains mainly the same features as a Wright machine. It has in front the elevator, which he can move with the wheel there. It has, except instead of warping the wing, it has separate aileron surfaces on both sides, which is the same as the wing warping, and has back there the rudder, and has also a pusher propeller. But he took off from wheels. Now, this was the most successful American besides the Wright brothers. In Europe, this was mainly the success, and the progress in flying was mainly done by the Frenchmen. And this represents here a model of the airplane of Henry Farman, who made with this airplane the first flight in one circuit of the length of 1 kilometer in the early days of 1908. I think it was in January. This machine had no lateral control. It had only the elevator in front and the rudder at the rear. And he tried with the dihedral, you see this has a little dihedral, with the dihedral to make turns only with the rudder, which was quite difficult. It is propelled by an 8-cylinder Antoinette engine, which had 50 horsepower, and you see again the features which they had taken from the Wright brothers, the elevator in front and the biplane design. Now the tail must remember you on the tail of a kite. You know, the Hargrave kite, the box kite, was in some way also a model of the first airplanes, or at least some people derived from this type of kites their airplanes, and in this way they had such a surface back there. Now, besides of Farman, the most successful Frenchman was, as you know, Louis Blériot, who in 1909, with this little machine, which is much smaller than all the other early types of aviation, crossed the channel from Calais to Dover in, I think it was July 1909. Now, this machine is different. You see, it is a monoplane. It had also the wing warping and has a tractor propeller driven by an Anzani engine of, as I know, about 25-30 horsepower. This engine, air-cooled, was not a very reliable one, but at least he could cross the channel after a rainstorm, cooled his engine in such a way that he reached the coast on the other side. He wouldn't have reached it if the rain didn't cool the engine. He had contributed to aviation one very important thing. You see, he had a stick. Instead of having these handles that all these others had, he had one stick, a wheel with a stick, and on this, the wires which go to the surfaces. And by moving the stick around, he controlled this airplane. Therefore, he is in some way the inventor of the modern type of airplane control. Now, I can only tell you a little bit about these early flights and these early developments. But if you are more interested, and you should be, in the history of aviation, which is so exciting, you might find a very good source of information in these books, which I have here. At first, these are the papers of Wilbur and Orville Wright, which were now printed and edited by McFarland from the Aeronautics Division of the Library of Congress. This is an exciting story, and even if this is a big volume, I will tell you that you read it with more interest than the most exciting mystery story you ever have read. Another book which tells in a very nice manner about the first time of aviation and about the performances of the Wright brothers and also their personal life, which I cannot mention here, is this book from Fred Kelly, The Miracle at Kitty Hawk. In our next lecture, I will tell you something more about the discovery of the dynamic lift. That means of the evolution of the cambered wing section. To give you just a little glimpse in what we will see, I have here in the tunnel one of these sections, and if we have the smoke lines on, then we can see the flow pattern, which we will discuss in our next lecture. Until this time, goodbye and auf Wiedersehen. In the previous lecture, we have talked about the invention of the airplane. And we were going through all the different stages of this development. We have seen that three major problems had to be brought to a solution. The first problem was the lift problem. That means to make with proper wings or any kind of surface enough lifting force so that we could carry the airplane aloft. The second problem was the problem of control. That means to design a certain system where we could keep the attitude of the aircraft in a proper position and go with the airplane according to the will of the pilot. The third problem was the problem of propulsion. This problem means that we have first an engine and on the other hand a propulsive system like propellers and other propulsive devices. And we have to invent and to design this. If we solve the three problems, we can build an aircraft. Now, they are certainly of equal importance, but you might admit that if we did not solve the problem of lift, the work on the two other problems wouldn't have been of much value. And therefore, since lift is a major problem of aircraft invention, we will talk at the present time about the dynamic lift. Now, we know not much about any activity in the early times of history, and we have only a few sagas or something like this, which are 200 or not true. The only man who really was working on this problem in a more modern way was the great genius of the Renaissance, Leonardo da Vinci. And I will give you here some quotations from his books, which actually are a big volume, and we can only take a few remarks of this great genius of the Renaissance.
The pressure exerted by the wings on the air is the same as the pressure of the air around the wing. Can't you see how the wings of the eagle striking the resistant air sustain his flights in the extremely thin air at high altitudes? You see how the wind over the ocean, repulsed by the full-blown sails, speeds up the heavily loaded vessel. From these proofs, you can conclude that man, too, will be able to master the resistance of the air. With large wings skillfully designed, he will exert the pressure on the air and master its motion so that he will be able to lift himself from the ground.
The work of the great genius Leonardo da Vinci was lost. And when the Frenchman Montgolfier invented the balloon, the lighter than air, most people thought that this was the solution of human flight. It took quite a while until people had to realize that a balloon itself is certainly a very fine instrument for investigations, but it's not the solution of the human flight as we have it today. And physicists began again to search for the true source of the dynamic lift. The first instrument which was known to men, which would fly as the heavier than air, was the kite. We don't know exactly who invented it, but in the last centuries, the kite was used as an instrument for research in the atmosphere. Such kites were developed by the Australian Hargrave, and we have a little box kite here as a model in the wind tunnel, and we can see how it flies. When I turn the wind on, the kite goes up. I turn it down, the kite falls down. There it is. Again turn it up, and now if we introduce the smoke, we can actually see how the flow around the kite behaves and why we get this lift. The lift force itself is indicated by the direction of the line which holds the kite. We see that a certain pressure on the surfaces of the kite gives this lift. We will see that even better if we only mount one flat plate into the tunnel. Now we have a flat plate in our smoke tunnel, and we see that if we have no angle of attack, that means no angle between the plate and the flow line, we certainly have no lift. If we turn the plate up, we see that the flow is slowly deflected downwards and a lift results, which is mainly created by pressure from underneath. If we turn it higher, we see very well that behind the plate on the upper surface there is a dead air zone behind the plate, which comes out even more if we turn the smoke down and observe now when I start the tunnel again, as this. When we turn it more up, then violent oscillations begin, a phenomenon which we will mention later in another lecture. This example was used from the famous scientist Helmholtz and Kirchhoff as the first example of explaining the lift, the dynamic lift, on the flow of a flat plate. They took this example where we have here a dead air zone and the flow goes around like this. Now, it's obvious that if you disregard the friction forces, the pressure necessarily must act perpendicular to the plate and causes a lift force which is also perpendicular to the plate. If you resolve these forces in the resultant force in a lift force which is rectangular to the oncoming flow and a drag force which is in the direction, then you see that you can, from calculating the resultant force and knowing the angle, we can find the lift and the corresponding drag. From this theory, which I can explain here only very short, it was concluded that to fly a heavier than air, a considerable amount of power would be needed. When we take, for instance, an 800-pound aircraft with a man in it and a machine, and let's figure out a man would probably weigh 200 pounds, and we would have probably 200 pounds structure. Then we would need an engine of 400 pounds, which on the basis of the theory should develop 100 horsepower. Now, at this time of the theory and of this early development, which was 1870 around, no engine was known which would give so much power for just so few weight. Heavier than air will not fly. This was the conclusion of the theory. And if there wouldn't have been any independent thinkers who still searched for other means of dynamic lift, this probably could have been the death sentence of aviation. Among these were two young engineers who were lovers of birds and observed all kinds of birds, and among them the big water birds, the storks, which gave them the possibility to see more clear what the action of the bird's wings would be. Now they tamed some and measured them. And so they came out that such birds, which they had, would weigh 8 pounds. The bird. And the theory, as I explained it before to you, stated that we needed for each 8 pounds 1 horsepower to fly. So this birdie should have actually 1 horsepower. Now it's obvious that this couldn't be, because the natural horsepower weighs about 800 pounds. And if you think that a bird would have probably a more efficient muscular system and other advantages due to its smaller size, you could probably reduce this weight ratio of 1 to 100 into a weight ratio of 1 to 10, a power ratio of 1 to 10. Well, and you could conclude from such estimation that this bird would then have probably 1/10 of a horsepower for horizontal flight. That means the Lilienthal brothers concluded that natural flight was at least possible with 80 pounds per horsepower. Now, there was no theory known at this time where you could derive such a thing. The only way to prove their point was, again, the way to do experiments with wings like the wings of birds. And there Lilienthal built himself a kind of a whirling arm, which you see here in this picture. And there he measured first the straight wings, and then he began to measure cambered wings. That means wings which are hollow in its cross-section. This is straight and this is cambered. If you look at the bird doesn't have straight wings. The bird has cambered wings. That means they are hollow underneath and rounded above. And when you now observe in our smoke tunnel the flow on a cambered wing, you will see at once that this is so much more advantageous compared with the flat plate. The cambered wing guides the air over the upper surface very smoothly, and we have no dead air zone above and behind the wing. When we now turn the angle of attack to higher values, then we see that the upper surface begins to stall, as we call it, and again the dead air zone, as we know it from the flat plate, develops. But when we turn the angle of attack down to 0, that means to a position where leading and trailing edge are at the same level, we see that still the deflection of the flow is there and we have lift. This was one major point of Lilienthal's investigations, which showed that the original theory could not be right, who explained the lift as pressure from underneath. The main lift must be the suction, the low pressure developed on the upper surface. And to prove this, he used a little simple gadget, a propeller, or might be called a helicopter rotor, which is completely flat underneath and has a cambered surface above, a cross-section like this. Now this can move in this or this direction and gives lift. So if I turn it here, you will see that without angle of attack we have lift. Now watch this. He published all these tests and his observations on bird flight in a book, The Bird Flight as the Basis of Aviation. But even if a thorough investigation of his work would have shown that he discovered the real source of dynamic lift, nobody paid much attention to this publication at this time, which was 1888. He couldn't do much about it. And what did he do was to build the first man-carrying heavier than air aircraft, to build gliders, with which he could fly from a hillside downwards, gliding through the air with the power of gravitation, like a sleigh on a hillside, and measure the gliding angle, measure the speed, and in this way establish the power which was necessary to carry such an aircraft in a horizontal course through the air. He didn't want to do only this. He wanted also to imitate the soaring flight of the birds on the upcurrent of a hillside. When you have here a hill and the wind is blowing against it, then you have an upcurrent. And in this upcurrent, you could fly with your glider without losing any height. He tried this several times and improved his gliders, and finally found that he needed more and more wind. And on one of his last tests, which he wanted to do with this machine, he went out in a strong wind, and since he didn't care very much for the control of these gliders, he actually controlled them with shifting his own weight. He was caught by a strong gust, thrown up 100 feet in the air, lost control, and dove to his death. Before he lost consciousness, he uttered the words, "Sacrifices must be made." How many courageous men have since this first accident on a test flight given their lives for the conquest of the air? On their sacrifice, our knowledge is built up. And scientific achievement is not only accomplished by the men on the desk and in the research laboratories, but by the heroes of aviation who paved the way for this new conquest of the air. The final theory of the dynamic lift of an airfoil was developed by the two scientists Kutter and Zhukovsky. Kutter, a German, and Zhukovsky, the father of the Russian aeronautical science. A modern wing section is never a thin cambered plate, but it is now a streamlined cambered plate to give space for the elements of construction which are in such a wing, like the spars and other construction elements. You can easily imagine the shape of such section if you think that we first have a streamline like this, actually what we call today a symmetrical airfoil. And if we bend this, then we get a cambered airfoil like this. We have now installed one of those airfoils actually between this one and this one in our smoke tunnel, and here it is. You see, due to the rounding of the nose, the flow goes smooth over the surface, and even if we increase the angle of attack, it still holds on the upper surface. Our stalling point, which was originally much lower, is now put into higher angles of attack, which makes it possible to fly at large speeds and low speeds. Well, the main lift, as we have seen it before, was the suction on the upper surface. And this is caused by a higher speed over the upper surface, which you can see here from the narrow streamlines. But you can see it much better on a high-speed movie, which we might show you now, which is made with so-called pulsating flow. That means we enter into the tunnel pulses of the smoke, which we interrupt periodically, and this timeline, which goes now over the wing section, shows us the difference in speed on the upper and the lower surface. I think this picture speaks for itself. The death of Otto Lilienthal caused many investigators to take up the search, the development of gliders and the further test of airfoils as proposed by Lilienthal. Among them were the two young Americans, the final inventors of the aircraft, the brothers Wilbur and Orville Wright from Dayton, Ohio. With great ingenuity, they tested gliders and they built themselves a wind tunnel and made in this first successful wind tunnel many experiments on different shapes of wings and airfoils. Unfortunately, these tests were not published until after the death of Orville Wright and are now composed in this big publication of the Smithsonian Institute, a very valuable book. At the time they tested this, the case Lilienthal against scientific theory was not yet solved, and they had to decide whether or not the negative tangential force, as Lilienthal pointed it out, existed. What is it? See, the original theory pointed out that the force, the resultant force, is rectangular to the flat plate. So lift and drag can be calculated from this. Lilienthal showed that the drag is much smaller than predicted by the theory. That means that his resultant force he measured is ahead, in front of the perpendicular line which you draw towards the so-called chord of the section. Then when you resolve it, then you find that in this line of the chord is a force which points forward, the so-called negative tangential. Now, this is proved by the measurements, but to prove it to you here, I have a little simple experiment in this tunnel where we have a wing section on rails, and when I put the wind on, I turn the wind, then what happens? If the negative tangential exists, then this airfoil should run upwards on the rail against the wind. Now watch it. And there is a proof. If we have a little smoke, then we can even see it with the smoke lines, like this now. Well, this final proof of the tangential and the small tangential showed to the Wright brothers that it would be possible to design an aircraft which would carry a man. The famous flights of the Wright machine, December 1903, were made with a power loading of 63 pounds per horsepower. The next time we will talk about the control system of aircraft. And from the invention of the Wright brothers, we will go through the different systems until we show how a modern airplane is controlled. Today, we want to talk about stability and control of an aircraft. You know, it is often said that if you have an engine with enough power even you could fly a barn door. Now, I must doubt that. Well, I couldn't make the experiment with the barn door right in here because I fear the barn door is too small for this place. But I could probably take this cardboard as a model of a barn door. And we can try to fly this barn door model. And you will see how it flies. Well, I think the barn door does not fly. Even if I give him a push, it makes only erratic motions and falls down, but it does not fly. See, this is an important point. Something which moves through the air, we call it flies. And some other thing, we say it falls or it is thrown. What's the actual difference? When something flies, then we expect to have a steady motion with almost uniform velocity, and where this thing which flies keeps the same attitude all the time. Something which is thrown might change its attitude, it might change its course, and do erratic motions. Well, I can explain it in a very simple experiment to you. See, I have taken from my desk calendar 2 pieces of paper. The one piece of paper is just this one. You see, when we let it go, well, it makes these erratic motions in falling down, as you see with any piece of paper, you know. Now, if you fold some part of this up so that you get a special position of the center of gravity and shape it a little bit different, then you can make it flying. You see here? That means, what do you need for flight? You need stability of the motion. And on the other hand, if somebody would be in there and he doesn't want now to fly this way and probably around like this little model does it, but he wants to go another way, or he wants to go up, wants to go down, then he has to have, besides of the stability, he has to have control. So what you need is stability on the one side and control on the other side. Now when you think, which of the two is the most important? Well, on vehicles, as we use them like a car or a bike, we actually don't have stability. We just control all the time the car to go straight on the highway, or we control, for instance, the bike by hand or shifting our weight. So if we have an efficient enough control, we could all the time keep this flying thing on an even keel. The problem is this, that while we are on the car, for instance, we have to control only one motion sideways. But if you are in an airplane, then you have to control 3 types of motions, since you have 3 degrees of freedom. See, you have the freedom to go up and down. You have the freedom to go left or right. You have the freedom to go rolling. That means turning in the direction of your axis. Therefore, since you have 3 degrees of freedom, you need 3 types of control. And it would be pretty difficult for somebody now not only to control this, which is probably done with a stick on an aircraft, but to control the up and down motion and to control the roll motion, all in one time. Therefore, finally, we came to the solution that the best is to make an aircraft stable in itself, inherent stable, and then control just its motion from there on. But originally, most people thought that flying, this time gliders, since they didn't have engines as yet, you would just need to shift your weight. Shift it forward and backward so you would control the up and down. They never thought about the control of the roll. And the first people who ever conceived this idea that you need 3 types of control for 3 degrees of freedom were the Wright brothers. Now they said we must change the incidence of the wings, the outer wings, so that we can turn in rolling over, because when we make a turn, then we have to bank against the centrifugal forces, which would throw us out. So first they thought the easiest way to do it would be probably to make a mechanism so that the wings could tilt and each wing would have a different angle of attack than the other one. But this was mechanically too complicated, would have taken too much weight. So they came to a better idea and said, why we don't take the biplane type and twist the whole frame. See, I have here a simple model, actually a replica of the first kite model which they tested. And see, they did not have any bracing across in here. They're just bracing in front, bracing at the back. And in this way, when you now make wires over rolls which are actuated by the pilot, then you can twist this without changing its strength. You see? And this type of warping the wings, they use all the time on their gliders. Now, I have here a very nice model of their 1902 glider. Actually, an exact model as the glider looked like. And we have even in here built in the controls as they used them. This is, now the pilot itself lays down on this lower wing and has in its hand the elevator control, which is this one. You see it move? So he pulls back and the thing goes up. Now he has a cradle where he lays in, and when he shifts this on left or right, then the whole wing warps. I hope you can see it. This warping is actually not very much what you need there. You see, when I warp it this way, then this angle is smaller, while this angle is larger. But they met in this way one difficulty. The moment you warp, for instance, this so that this angle is smaller and this is higher, that means that the plane would roll over this way. Then, due to the higher lift which you have here, you have more drag. And this more drag would actually try to turn the plane against the rolling. Therefore, they used, in addition to this wing warping, they used a rudder which is directly connected with the wing warping, so that when you push this wing down and have here more lift but also more drag, the rudder would counterbalance this more drag by turning the aircraft in this way. This very intelligent method of controlling an aircraft was actually the solution to the invention of the first flying machine. Now, most people would think that such a control in front for pitch, that means for longitudinal motions of the aircraft, would not be stable. you have to control all the time. Actually, that is not so. You can make an aircraft flying stable in pitch with an elevator, as we call it, in front or at the rear. And in both cases, you can obtain stability of flight. As I can show it you here. See, I have here a little tiny, flimsy model where I have the additional horizontal surface, the so-called elevator, in front. And you will see that this flies very nice and stable. You see? Now, if I take this wing and just turn it around, like this. You see, I have some clips down there, which I can push on this little stick. And then change the center of gravity by putting some little weight in front. So, and if I have it now, adjust it right, I think it should be, then you can fly it this way. You see? That demonstrates very simple that you can stabilize for pitch stability either with the surface at the rear or with the surface in the front. The main principle of this stabilization is this. The surfaces which are in front have to have the higher specific loading all the time. That means if you have a wing, for instance, which has 30 pounds per square foot wing loading, and you fly with an elevator in front, then the elevator in front has to have more than 30 pounds, let's say 45 or 50. If you have it in the rear, then you have to have less than 30. That means probably 15 or probably even nothing. This is the system of pitch control. And even if you have only a wing, a flying wing, you do still the same thing. See, this is the model here. Now, the surfaces in front are the surfaces at the center. The surfaces at the rear are the surfaces on the wing tips. Therefore, you have to have less loading on the wing tips than you have in the center, which you establish here by just warping this wing, as you see it here. When you look from the side, here we have a much less angle of incidence than we have at the center. And you will see it certainly flies nice and stable. See, there it goes. Now, at our conventional type of aircraft, we have now established the pitch control by surfaces at the rear, which is in many ways more practical. You have to have a long fuselage, and you have practically no loading on the surface, on the elevator surface, makes it more sensitive in flight. And I have here a very nice little model where we now can explain all the method and all the system of controlling an aircraft as it is today. You see, this is the seat which is open here. Let's say it looks like a glider. You sit here and you have this stick in your hand and you have your feet on the rudder bar. Now, with the stick, you control with forward and backward motion the elevator, which is now a flap on a fixed surface, which we call the stabilizer. You see, when I move this back, you see, then the flap goes up. When I move it forward, the flap goes down. Now, if I move this stick sideways, then I move the so-called ailerons, which now replace the old method of wing warping as it was done with the Wright brothers airplane. Since we have now stiff wings and we fly with much higher speed, which is necessary then to have stiff wings, then you couldn't warp these stiff wings. That would be very difficult. Therefore, we have a hinged flap on the outer part of the wing and move the hinge flap instead of turning the whole wing. And you see, when I move this stick now sideways to the left, then the left one goes up, the right one goes down. You see, this way. Now, if you fly this aircraft and you fly through gusty winds, what have you to do? You see, you just do nothing, then keep the stick in a vertical position. Then you do the right motions intuitively. You see, if a gust hits our aircraft and pitches it up, well, then I keep the stick straight up and my elevator is down, so it would lift the tail back. If it would go this way, it would push the tail down. If I would be banked by a gust from the side, then due to the banking and keeping my stick straight, this aileron is up, pushes the wing down. This aileron is down, pushes the wing up. On the other side, if I want now to move the aircraft around, then I have to do just as if the stick would be fixed on the aircraft and I want to move the whole aircraft with the stick. So if I want to go, for instance, into a left-hand bank, then I would take the stick and want to move it this way. The moment I do this, I lift this aileron up, this down, and the left bank is there. If I want to turn it, then I have to use combined rudder, which I have on the feet. That means I make a left turn, then I push the left foot forward and push the stick over to the left-hand side, and there is my turn, as you see it here. You see, this system is actually very simple, and you can conceive it intuitively. You don't need to think about it, and this is important to fly, because when you fly, you have to think on other things, and you're controlling which you do without thinking that you do have to do this. You do it just intuitively. Now, a large aircraft, as we have it now, wouldn't be very easy to be controlled by hand, because these surfaces have quite some pressure on it, and therefore we need some help to move the surfaces. So we have servo mechanisms and servo motors in between, which are controlled by the control itself or are controlled by an autopilot. This autopilot I can show you. You see, at what we conceived here and what we have shown is that when you fly through disturbances, the only thing you have to do is hold the stick straight up. Keep it always in a vertical position. If you do this, then the aircraft would by itself do the right motions. Now, to show you a simple model of the system of an autopilot, I have here a little arrangement with a free gyro in it. That means this gyro is on two gimbals. It can move forward and backward and sideways by itself. And when you wind it up with a little electric motor, and down here is a big wheel which makes actually the gyro, we have then an artificial stick, or what we could call also an artificial horizon. So if I now move this model all around, you see the gyro keeps this stick all the time straight. And this system of a free gyro is the heart of an autopilot as we have it in the large aircraft. We use it also in the same way for having an artificial horizon so that the pilot can fly without any visibility. You connect this gyro with little wires so that he gives signals to servo motors which then operate the controls. You see? You shouldn't upset it. Now, to show you the action of the control system as it affects the flow, we have some models in our smoke tunnel. And at first I want to show you the action of a usual elevator or pitch control system. You see, I have here a model where the wing itself is not attached to my controls. I can only move this little flap back there, which actually is the same as an elevator flap. And you will see that I will be able now to turn the whole wing just by moving this flap. Let's put it back into the tunnel. So, and close the window. And when I now turn the blower on, I can demonstrate to you how this acts. You see, I have here this one control wheel where I can now turn the elevator up and down. You see, when we have now the wind going and I turn up, elevator up, then we increase the angle of attack. If I turn it down, I decrease the angle of attack of the wing. And I can do any adjustment of the attitude just with this little flap. If we now turn the smoke on, then we can even see it with the streamline around this simple aircraft model. You see? Now I decrease the lift. Therefore, our stagnation point sits up here. We have practically no lift. I turn it up and the lift is increasing. You see how much curvature we have up here and how high the velocity gets on the upper surface where we have then the suction. Another thing, it's interesting to see here, the change of the attitude changes not only the field behind the model, but the whole field. And it reacts for our eye instantaneously. Now I have another model in the tunnel which represents the aileron system. That means just a simple wing section with a flap back there, which I can also move with the controls. And if we take this model out and put it in, I will demonstrate to you that such a flap works the same way as if you would change the angle of the whole airfoil. Because when you move the flap down, actually you make more camber, and then the angle of attack is this way, while it was before this way. So you increase the angle of attack and you increase the camber, and in this way you increase the lift, or you decrease the camber and decrease the angle of attack, and then you have down lift, or practically negative lift. So if we put this in there and see it with our smoke lines, then we can at once observe the action of a flap as it is used on ailerons and certainly also on the elevator or on the rudder, in this way on the symmetrical section, while this is the wing section. Now let me adjust this. You see, I have to move both wheels when I want to change the angle of attack. And when I move only this one, then I can turn the flap itself. Now let's have some wind on and some smoke. This would be, for instance, a position of normal flight. You see, if I now turn it down, we have much more lift. If I go up, we have practically no lift. And you see also again how instantaneously the whole flow field responds to such motions. The motion is also the same if I have a larger angle of attack. The next time we want to talk about the propulsion systems which we use on aircraft. And I want to show to you, just as an introduction of this program, a picture which we took long time ago of a jet taking off. It's actually taken in 1941 of the experimental high-speed aircraft, the 163A, which I designed in way back 1938. You see, with these modern propulsion systems, we could have a very high performance, and actually we flew with this aircraft in 1941, 630 miles per hour. Now, I will also show you several models and other arrangements in the wind tunnel and here to explain to you the system of propulsion as with propellers and jets and things like this. For today, goodbye and auf Wiedersehen. Let me tell you a little fairy tale. Once there was an old windmill, and when the wind blew across the country, its arms moved around and around, and it worked for all the people in the country. And this went on for a long time. But finally there came a smart man, and he, believe it or not, took the windmill off and made a propeller out of it. Now, what is a propeller and how does it work? Well, we could, for instance, imagine it as just wings. Instead of going each one forward and making lift, they go around. And while they go around, they also produce lift. And this lift of each of these wings is transmitted to the shaft, and on the shaft it gives then what we call the thrust of the propeller. Thrust and lift are actually the same thing. On the other hand, since now such a propeller has the task to pull an aircraft through the air, this propeller moves not only around, but it moves also forward, and it screws itself into the air. If you would think the air would be a solid matter, then each revolution would give the propeller a certain amount of forward motion, what we call the pitch of the propeller, like we call it a pitch of a screw. Well, therefore, now, this wing couldn't be just straight, but it should be warped, because the outer blades make a much larger peripheral way, while all the inner ones make just a small one, while all the parts have to go with the same speed forward. Therefore, it is a wing on a spiral surface. Here you see a spiral surface like this, and you can imagine that each of these little sticks represent the position of a propeller blade while it goes once around. And we have to put then the propeller on such a surface which is here steep and there gradually or more flat. We can see that also if we take a propeller model like this here. Look at it. You see that this is warped, and we have inside the steeper angles and outside the more flat angles. But itself, if we take a piece out, we see that each section looks exactly like a wing as we had our wings in the smoke tunnel. Now, to observe the action of such a propeller, we have here a model in our wind tunnel. This model is just a tiny propeller driven by a small electric motor. You know, we have only 3 inches width in this smoke tunnel, so this propeller is quite small. You see it here mounted in the tunnel. And when we now turn the electric current on, then you see it runs and draws the air through the tunnel. If we start now the tunnel itself and produces some smoke, then we see at once the flow picture around a propeller. Isn't it interesting? You see, in front, the air is sucked into the prop and is accelerated actually before it hits the propeller disc. And then behind it, it again is pushed out. So we have a pressure differential across the propeller which pushes the air backwards. You see it even probably better if we just cut the speed off and let the propeller itself make the flow through the tunnel. Now we can also turn this propeller and give him angle of attack, and then we have the action as a helicopter rotor, which is nothing than a propeller which is now inclined to make lift and propulsion. You see it here very well. And we also can take a little less speed that you see this action more distinctively. But the best we can see it if we look at a slow motion pictures which we have now here. There it is. There we see the propeller in the smoke tunnel and taken with high-speed pictures. We have also pulsated the flow so that you can see the velocity distribution across this propeller. Now we have the same propeller in an inclined position, and we see now very clear how we could make it lifting and propelling. You see, the shift of this timeline is actually the same as we had it with the high lift wings. That means we have lift here. And also thrust, since the propeller is inclined, so part of the lift is a horizontal component which pulls the thing forward. That is like a helicopter would fly. We have seen the last time at these pictures in the smoke tunnel that we can use a propeller not only for a propulsion device but also as a lifting device And we have even seen this in the slow motion pictures with the pulsating smoke, how the flow went over and gave lift and forward thrust. Now here we want to make a little test to see how much such a propeller would lift. We have a little model propeller here driven by an electric motor, and this is fastened to an arm which moves around here. And there we have a weight which we can shift so that we can finally load the propeller so much that it just barely lifts this weight. Now let's turn this prop on. You see, I have here a power supply, and we can see here the voltage and the amperage which we put in this little motor. You see, now it has about 10 volts, 15, 20, 25. There we are. So it lifts at 28 volts. You see it floats. Now you can shift that weight over there and give a little bit more power. Now let's shift the weight further on. And still lifts. Now let's put the weight here. There we are. Have it so loaded, so much loaded, then it wouldn't lift itself anymore. So that's the limit with all the power on. As you see, 33 volts. Now, can we do better? That's the question. Well, let's think about it. First of all, you see, when this propeller turns around, then it makes pressure underneath and suction above. That means it has a differential pressure across its disc. And since there is open air on both sides, this pressure on underneath will equalize against the suction which you have above, and you will have a flow around the peripheral line of this disc. So you lose some of the pressure which we have from underneath. What could we do about it? Well, if we put a tube around, then this pressure could not equalize around the tips, and we would have more lift of such a propeller. We should house it. Such a housing we call a shroud. That's like this piece here. See, and we can put this shroud around this propeller and then try whether we wouldn't have more lift if we put the whole thing in a tube. You see, we can put it over here. And we can try how this propeller within the shroud would lift. Actually, I have the weight at the same place where the open propeller didn't lift anymore. And I have put the shroud on it, which also weighs something at least. Now let's try. You see, we begin with low power and turn it up 15, 20, 25, 30, 30. We don't even have the full power on, and it lifts. That means we have increased the lift of the propeller considerably by putting just a shroud around housing it. Actually, this lift increase in a larger scale is in the range of 60% more lift. Now, to explain it to you more particularly, especially the flow condition which we have around such a shroud, we can see again a shrouded propeller in the smoke tunnel. So we have put a little shrouded propeller in our smoke tunnel. Actually, that is the propeller model which we did have before, you see, and on both sides we have put a wing-like section on it so that we have a channel through which the flow has to go now. We couldn't make a round shroud, otherwise you wouldn't see the flow inside. Now let's start the tunnel and the smoke. And we might see then how this propeller works. Here you see it first without the action of the propeller. You see that there is quite a bit of drag behind it because that wake shows that there is turbulence which makes drag. Now if we start the little propeller, watch this. Then, as you see, large part of the air is drawn into the thing and accelerated, and also the outer streamlines come near to the sections so that we have practically no drag due to turbulence over the shroud. We can even see it better if I stop the smoke as it looks here, to see how strongly this pulls. And when I turn now the model, then we can see it, how it would work with an angle of attack. So as a propulsion and lifting device. But all these actions you observe even better if we go back to our slow motion pictures. And there you have it. Here first, the action of the shrouded propeller as a straight propulsion device giving only forward thrust. You see how the air going towards the shroud is propelled because our timeline bends forward in the center. Now if we have it inclined so that you see at once the velocity field around such a device, and you see very clear that we have lift as we had lift on the wings because we have the shift of the timeline. You see on the other hand how this air which goes through the shroud itself is propelled and comes out much earlier, the little smoke cloud, than the other smoke from the timeline. We see therefore that such a device can be used as a lifting and propelling agent for an aircraft. The shrouded propeller is the simplest example of what we call an internal flow system. That means a flow which now is completely enclosed. And since we have it enclosed, we can guide it as we want it. And as we have seen, first of all, it is the most efficient lifting device. On the other hand, it is also high efficient in forward motion. Well, this brought me to an idea to take the shrouded propeller as the design element for an aircraft which would fly now without wings. And we call it the Aerodyne, that means a dynamic flying airship. Just look at this little picture here. I will explain it later to you more carefully, but to give you a glimpse of it, there our Aerodyne model consisting of a row of 4 shrouded propeller flies through the hangar in a test flight. It's propelled by 4 electrical motors, as you have seen it here in our little model. We can use the propeller also for another purpose. You see, we have seen that when we put the propeller in the tube, we have a larger pressure differential across the propeller. And if we make a very efficient propeller, then what is it? It is actually nothing than a compressor. Now, the main thing is that the pressure differential is as large as possible, and therefore, instead of using just 2 blades as a usual propeller has, we can use several blades which then cover most of the area of the propeller disc, as you see it here. We have here a tube with electrical motor and a little multi-blade propeller, which we also call an axial blower or a one-stage axial compressor. You will see that with such a device, you can even get a, well, good pressure differential in one stage. I will show it to you here. See, we have here our pressure gauge as we used it before. And if I turn the power on, then we can read the pressure differential across the propeller. See it here? Now I turn the power on more and more. And you see it gives a nice pressure differential of about 2 inches of water. And if I close it down so that less air goes through, then this differential gets even larger. Now what we do here with one stage in a simple little model, you can do in larger size, and you can put several of these compressor stages behind each other, and in this way create a large compression. And when you then take the air which you have compressed, heat it up and blow it through the turbine and let the turbine run the compressor, then you have what we call a jet engine. A jet engine is actually nothing than a multi-blade shrouded propeller, which is here called the actual compressor. This is this part of the jet engine. Now, due to these many stages, there are jet engines up to 14 stages in this compressor. You get a large pressure ratio from the inlet to the outlet of the compressor, where we now blow the compressed air into a combustion chamber, burn it, increase the volume, and then blow this hot gas against a turbine, which takes part of the power out of this heated flow, turns it back through the shaft into the compressor so that you drive the compressor with this part of the power, and the other power goes out as the jet stream. The thrust actually is produced by the compressor part of the jet engine and partly by the inlet. I will not go too far into the explanation of this process, which is actually in many ways more thermodynamics than aerodynamics. I just want you to realize that a jet engine is actually also a propeller device, since it has these compressor stages, which are nothing else than a multi-blade propeller. Now, to show you such action in the smoke tunnel, we couldn't put such a device with these many blades in our tunnel, and we have made this simpler. We have made a small model of a jet engine, the cross-section of it, and instead of driving it with such a complicated device, we have a little jet stream in it. Now here we have the model in the wind tunnel, and at the present time the blower is not yet on. Now let's turn on the blower, and you see at once that the propulsion which we have inside gives us a strong stream behind and also pulls all the outer air towards this body and smoothes out the flow. A very interesting effect. You see, when I turn the speed down, then even this effect gets stronger. Now we can also show it with angle of attack, and there you see it. But the better representation is when we look at the slow motion films of this device. Now we see the jet model in the tunnel in a straight attitude, that means with no angle of attack. We took this picture with the so-called pulsating smoke, and you see in this way very well the velocity. First of all, you observe that the stream which goes in there comes out much earlier due to the inner propulsion. You see now back there this puff coming out. And on the other hand, you see how nicely the outer streamlines follow the outer shape of this jet. This is due to the fact that the jet stream back there stabilizes the flow. Now you see it with angle of attack, and you can observe the same effect. It's very stable and smooth. And on the other hand, you see now that we have lift, because we have this shift in the smoke front, the so-called timeline. That means we produce here not only the jet stream inside, but we also produce a lift due to the flow on the outer surfaces of such a propulsion system. That is also used to make what I told you once, this aerodyne. The last of the propulsion systems which we want to mention here is the rocket engine, which will probably carry men into space. It can therefore not be an air-breathing system, but it must apply the oxygen and the fuel in two different lines which come into a combustion chamber and then get burned there and blow out a high-speed stream into the air. You see such a thing here in the smoke tunnel. In our next program, we will talk about the drag as it exists on bodies and wings. And to introduce this to you, we have here a body in the wind tunnel where you see what we saw before, the big disturbance which is caused by such a body. But we have also done a trick. We have inserted here a little jet stream. And if we turn on the jet stream, you will see that we can reduce the drag. That means if we compose a body with the right propulsion system, we have an advantage of such a combination as you see it here. And this we will explain at the next program. Goodbye and auf Wiedersehen. Well, if we want to talk about drag, aerodynamic drag today, we must be aware that this is one of the most intricate problems in fluid motion. Many years of theory and scientific work was spent on this question, but we have still today basic problems which are not well explained. Now, if you think about the drag of a body which moves through the air, you would say, all right, the drag is caused by the friction of the air against the body. All right, but what is friction? Well, if you look it over, friction is the resistance between two bodies moving against each other. Here the air against the body. All right. Then the resistance is a drag. So there you are again. And what we have to do is we have to explain friction, aerodynamic friction. Let's see how we could do it. Well, we think, for instance, of, let's say we throw a stone. And think of this motion. Now, you might realize that if the stone goes through the air, there might be some air particles which are still attached to the stone. So the stone makes, while it goes through the air, a certain motion in the air. It propels a column of air which is behind the stone and runs then with the stone. So, well, if I can explain it to you on a blackboard, would be probably this. Here is a stone, and the thing is moving in this direction. Then we have a certain amount of air which is still attached to the stone due to the fact that little particles stick on the surface. And when the stone is there, then there is a column of air behind the stone which is filled with air which is moving also in this direction. The stone is moving in this direction, so the air is at rest. You can actually feel this if you, for instance, stand there where a train goes by or a car, and you can see it in the dust cloud which is behind such a car if it goes over some of our old travel roads. But you can see it even better if we look at the smoke tunnel. Now, I don't have a stone in the smoke tunnel. I have a nice, round, circular cylinder. But it is a good presentation and a good example to look at this. Here it is. Now, well, we see this piece of air which is more or less attached to the body. But we see one other thing, very peculiar. This is an oscillation in the wake of the body. You know, we call this part, this air, which is moving with the body, we call this the wake. Or let's write it here, the wake of the body, the wake in the flow of air. And in this wake, we have here apparently a very distinct oscillating motion. Now, we might not see it clear with this normal speed, but we can see it much better if we take of this flow picture a high-speed movie and then look at the high speed. And there it is. Now look at this. Isn't that fascinating? This regular motion of a generation of large vortices which are now coming off periodically, one at a time from the upper or from the lower corner of this round body. Such a phenomenon was first investigated by Professor von Karman, and therefore we call this wake, which we call also a vortex street, the Karman street. Now, the generation of these vortices certainly needs lots of energy, and therefore the drag is not only here friction drag, it's actually only a very small part of the drag, but the main part of this drag is caused by the generation of the vortices, because there is energy needed to make such vortices, and this energy must correspond to the drag times the velocity of this motion of the body through the air. Now, if you want to stop this, what could you do? Well, you could do one thing. You could probably make a plate back there on the body, which then separates both parts of the flow, and in this way damps out this oscillation. Well, let's try this in this tunnel. Now we have here that cylinder with a plate in it, which we call a baffle plate, so that we would stop the oscillating motion of these vortices. You can see it here very well. You see now this part is mainly uniform and there is no oscillation, but still at the wake far behind the oscillation begins. It actually is something which has some similarity to the scattering of a flag. And if you wanted to reduce now this large wake, which is still in here, and which gives us a dead air zone, which again would cause drag, we have to fill it out and make this part of the body. That means you have to do something here, so that you would come finally to a round piece which has a fairing behind. And if you smooth this out a little bit, then you get a shape which is approximately like this, and which we call a streamline shape. You will see this as our next test in the tunnel. And let's just put it in there. Takes just a few minutes to mount this streamline section, which you see here. You see, this is now derived from originally a round rod, which is then a little bit elliptical flared out here, but mainly has a long and smoothly decreasing tail end. This is much more important than this, because we have seen on the round rod that the flow here on the front part was all right. We had only trouble at the rear. So if we make a blunt nose, this wouldn't bother us. But we have to fare it out nicely and make a quite long tailpiece on it, so that the air can follow such a surface smoothly, like this. Now, let's look at this in the tunnel. Start the blower and the lights, and there we are. You see, now I might adjust this a little bit. You see that we have now stopped the vortex motion almost completely. And we have only a wake which contains now here air which moves with a lower velocity than the outer one, because due to the friction on this surface, the air which is narrow to the surface was slowed down and has lost a certain part of its momentum. On the other hand, we see that a streamline which is near to the body now suddenly begins to jiggle and to blur out. We call this the transition from a smooth laminar flow to a turbulent flow condition, which we may see even much better if we look now to pictures which we have made in our three-dimensional tunnel. Now, before we see these pictures on the three-dimensional tunnel, I probably have to explain to you a little bit how this tunnel works. You see, the tunnel which we have here is a two-dimensional tunnel. We call it this way because we have just a narrow strip of smoke or flow which is closed in by two narrow glass walls. Now, a three-dimensional tunnel is a large cross-section which is actually somewhat rectangular, and then we mount the model from one side of the wall, and here we have the flow through it. So this is kind of a box enclosed where the flow goes through. And the models itself, which you will see in these pictures, are, for instance, this straight wing. You see just a half of a straight rectangular aircraft wing, which is now painted black so that we can see the smoke lines very well, and we release the smoke on this leading edge. You see, we have very fine holes all along here and part of the holes along this tip, and we blow now the smoke into the model through this tube, where we also mount the model so that we can change its angle of attack. Another model which you will see is this swept wing model, which is mainly the same kind of construction, you see, with the fine holes on the leading edge. The smoke is introduced from the side into the hollow interior of this model. Now let's look at one of these pictures. We first see the straight wing mounted in the tunnel, and we see it with normal speed. When you see it with normal speed, you don't see much, but when you look at this picture now, where we have a high-speed movie or slow motion picture with about 1500 frames per second, then we see suddenly the transition between the smooth flow at the beginning of the surface and the turbulent flow, which is then at the rear. At the swept wing, we have in some way a different condition, because due to the swept back, the flow is not uniform all over the surface, but at different stations of the wing we have different conditions, which we see very well in one of the next pictures. This is this one. And there you see this wing from above. And you see that the transition at the outer part begins much earlier than at the inner part of the wing. Now here you see it from the side view. And I think you should observe this picture very well, which shows us so clearly that we have first waves on the surface, and then these waves overroll and finally break up like the breakers on a surf flow. and then the turbulent motion over the surface of the wing begins. Actually, this is not stalling. It still sticks to the surface, but with this turbulent motion. Now, to see this even better and to explain it more clearly, we have put a large straight wing in the 3D tunnel, and you see here a picture of this large tunnel, large wing mounted in the tunnel. You see it here from the side view, and it is just a picture to see how it is arranged. When we now look more close on this model, then we see again this wave motion, which is very distinct and actually is one of the most intricate problems of surface flow. Why is it so? Why are waves formed? And why are then these waves suddenly broken up into a turbulent motion? When we want to see this more clear, we can now look at one smoke ribbon. So before we see this picture of the smoke ribbon on the surface of the wing, I will explain it a little bit to you, because it's in some way difficult to see. On another way, this picture is a very important one and actually is the first visual observation of such a process. You see, we have the surface of the wing here, and we have a small smoke ribbon which just floats above the surface. Now, while it floats over, part of it is decelerated, it's slowed down due to the friction, so this stays back, and finally the outer part rolls over and forms here first waves. It rolls over, forms waves, and then rolls over completely from the vortex, which now disattaches and goes to here. And instead of now continuing as a vortex due to conditions of instability, this thing explodes and forms a big bubble of turbulence, a turbulence bubble which goes over the surface. Now, when you see this picture, you must think that since this is white smoke and we have a black surface which is very smooth, you see also the mirage, the reflection of this white smoke on the surface. So actually you see the smoke itself and its reflection. So don't bother. Now there's a picture. Only the upper part is the smoke and the lower part is the reflection on the black surface of the body. Here you see it very clear. This picture was taken with 3,500 frames per second. And we are actually very proud that we achieved this picture. I'm very thankful to the photographic department of the Collins Radio Company who helped us with this, and to my assistant, Mr. Schroeder, who made all the arrangements for this test. Now, if you see all this, and you see these friction on the surface, on this breakup of the boundary layer, then you think, what could you probably do to improve it and to prevent, first, a large turbulence, on the other hand, to reduce the total drag due to friction on such a surface? Well, first of all, you could do this. Since the lower layer on the surface is retarded and is practically dead air, you could suck it away. That means you could take a surface and have a little slot in it And when then this layer, which is retarded here, comes to this point, you suck it away, and a flow which has more momentum comes back on the surface. In this way, you would reduce the tendency of the surface flow to break up. Another method would be to do the reverse thing. That means you would make a slot here which would blow a certain amount of fresh air into this layer, and in this way propel it. Now we have here a model in the tunnel where we might show you how surface suction works. This model is a streamlined section, and we have slots in it, and through the slots we suck. Now watch it. When we turn the suction on, there it is. Then at once you see that the wake becomes much smaller, and you see also very distinctively the steps of this streamline where part of the dead air which is on the surface is sucked into the model. Now we have a blowing model in the wind tunnel, and I have made this extremely blunt. That means I have made a streamlined section which is really reduced to a very small size and very big, so that you might see how such action really works. When we, for instance, try now to turn on the blowers, then you will see that we can attach the flow, and we get a very nice and smooth flow over this surface. Even if I give angle of attack, then you see that the flow still holds on such a very narrow curvature of the body. You see, in this way you can reduce the drag considerably. The transition from this state with the large vortices and the suction we have also taken in a slow motion picture, which you see now here. And you might observe very clear the sudden reduction of this wake and then the close-in of the streamline. But when you think this vortex formation is mainly the major source of drag, and if we look at a wing, at a full wing with all its span in the tunnel, then you might observe another cause of vortices, which we will deal with in the next lecture, but I might show you just a few examples of this type of a flow. To show you this formation of vortices which make drag due to lift, we have here a model in the wind tunnel which represents a small wing. And you will see that if I increase the angle of attack and the lift of the wing, then you see suddenly a formation of large vortices from the wingtips. Look at this here. Why is it so? Well, it's due to the fact that we have underneath of the wing a higher pressure than above the wing. So on the wingtips, this pressure differential must equalize by flowing around the wingtip. And this flowing around the wingtip with the translation of the forward motion gives you a spiral motion which forms this vortex. Now if I give negative lift on this wing, that means if I turn it this way, then you see the vortex rolls the other way. But you can see this formation even better if we go to a model which shows us only the wingtip into the tunnel. Now you see this vortex formation on the tips of the wing cannot be done by nothing. You have to put new energy into the flow which makes the thing rolling. And this energy has to be provided by the propulsion system of the aircraft. This drag, which is caused by the wingtips, by this flow due to lift, is caused induced drag because it is induced by lift. Now we have this wingtip model here in the tunnel, and when we give angle of attack to the model, then you will see very clear how such a wingtip forms. I think it's quite exciting to see how nicely even such a flow line stays together while it turns violently around. You see, it is no friction there. It's just a rotational motion which is introduced here into the flow. Let's give it some more angle of attack. You see, this holds for quite a while together. But this is probably the normal position as it is formed on the wingtip. Now, in the next program, we will have many examples of this type of a flow phenomenon, not only on a straight wing, but on the modern swept back wing, on delta wings, and I will show you quite some exciting pictures on this matter. I hope you will not miss this program. On the other hand, we will have pictures from the 3D tunnel too. So, up to the next program, goodbye and auf Wiedersehen. In our last program, we talked about the aerodynamic drag, the air resistance. But the air resistance actually is not the only thing which you have to overcome with the power which you build into an aircraft. See, you also need power to make the lift. Two types of power you need. Power to overcome the air resistance, just to make it moving forward, and power to produce a lift. This is a difference between a land vehicle, like a car, or let's say a train, and an airplane. With a car or train, you need the power only to make the thing moving, to overcome the friction towards the ground and internal friction and things like this. And the weight is supported by the solid ground. But with an airplane, it's different, because when you fly through fluid matter, through air which can yield away. And in this way, you have to bring all the time new masses of air into play to be supported by a downward motion of these masses which continually come into the vicinity of your aircraft. You could probably compare this with a very simple example of a man who wants to cross a pond on some logs which are swimming in the pond. And let's assume that these logs are not large enough so that he could just stand on one of these logs. Now, if you think of this, we might sketch it just up. Then you have here, for instance, the beach on the one side, and then there are the logs in the water, somewhere around here. So, and on this other side is the other beach. Now this fellow wants to run over it. And while he runs over it, the logs give way. So actually the picture which you would make while he is running shows that the logs he just touched and is supported by them are underneath the water line. and the next one he just begins to jump on is beginning to sink, while another one he has just left comes slowly up. And here is this fellow now, which we might sketch in the simple way, standing up there or running up there from this to this. So actually the line of the logs, if you connect all the centers of the logs, is a curved line. And this fellow has to run all the time uphill because the logs gave way. So the log on which he is standing is lower than the ones where he wants to get at. And he has to get up all the time uphill. So even if this whole motion would have no friction, he would still have to do work because he has to work uphill. And this is the same with an aircraft, because also the air gives way, and therefore when you have an aircraft flying here, let's sketch it up, might be this would be some kind of an aircraft. So then the air which supports this aircraft is in a downward motion on the spot where the aircraft at the present time is. And this aircraft, instead of flying in air which comes direct against it, has to fly in air which comes above. So that even if you think of this being so smooth that there wouldn't be any friction, you still have to work because you have to fly actually against air uphill. And in this way, you have to do work. Now, this is a general concept of what would happen and why you have to do work to produce lift. But if you look at this process a little bit more specifically, that means look at the wing itself and at the motion, what would be around the wing, the motion of the air, well, then you must say, where does the air yield away? Now let's look at the aircraft, let's say from in front. Here's the fuselage. So now since this aircraft is supported by the air, you must have a pressure differential across the wings. So underneath of the wings, you have apparently positive pressure, as we have seen it in this tunnel, and we have demonstrated it. And above the thing, you have negative pressure. And this pressure differential supports you because pressure underneath, suction above, gives the lift. But what happens on the wing tips, on the corners, on the edges? Well, there a mass of high pressure air meets a mass of low pressure air. And since plus goes to minus, the higher pressure air wants to flow towards the region of lower pressure air. This floats around the tip, and this floats around the tip. And while you are now in forward motion and have this motion around the tip, the resulting motion of these air particles is what? A spiral. And if you look at this from in front, you are flying this way, let's say, then you would have here a motion of the air which comes around and goes backwards, and this backwards motion gives you what we call, well, what do we call it? A vortex. And these vortices are originated on the wingtips of the aircraft. And they produce this downward motion of the air we talked about before. But even if we probably go a little bit more deeper in this problem, we like to see it at least in the smoke tunnel. And I have here a model of a wing. You see, this is a plain straight wing. These are the two tips. And I put it in this way. And I have here a gadget so that I can change the angle of attack with these controls. Now let's put this thing in there. You will then observe one thing. Well, as long as we have no lift, we wouldn't have any pressure differential, because then pressure on both sides of the wing is the same. So result is that we wouldn't have any of these curls on the side, these wingtip vortices. If we have more lift, we get vortices. The moment we increase lift, the vortices must get stronger and stronger. And this we might see here pretty good. Now let's adjust this model. You see I have here two handles. The one is used to put the thing straight, and the other one is used to give an angle of attack. An angle of attack is this one here. Now let's put it, if we have now smoke, then we can probably see it. There it begins. Now let's put it first at an angle of attack where we have no vortex or no lift. That's this position, for instance. You see, the wake behind this wing is mainly due to the friction on the wing surface. We get then resistance. Now we change the angle of attack to a larger angle. That means we make lift, and there are the vortices. You see them very nicely. And even to see it better, we have another model, only the model of a wing tip. That means an enlarged piece of, let's say, this wing tip. And we can put it down into the tunnel now in this way, and can see the formation of the vortex even more definitely. This model we put now in the tunnel, this wingtip, is actually only half as wide as the tunnel itself is. In this way, we see kind of a three-dimensional development of the vortex in this small tunnel. Now I think the thing is in there, and we have adjusted it so that we have no lift. You see, then we have a little negative angle of attack. Now if I increase the lift, excuse me, it takes a little time there. Then you see at once how this vortex develops. You see very clear these curls, these spirals, beginning here while the flow goes from the lower surface to the upper surface. Here underneath we have pressure. Above we have suction. And the air flows from the pressure side to the suction side. Now it is carried away, and due to this rotation and translation, we get this vortex. It's interesting to see that this is not a motion which causes friction, because these lines stay very well together. That means it's a completely frictionless flow around the thing. But due to the production, to the generation of the vortex, you need a certain amount of energy. You see, you cannot produce just a vortex for nothing. You put this rotation into the air, and the amount of rotation takes away a certain amount of energy, which you have to counteract with the power in your aircraft. Now, when we put this in negative angle position, you see, go through the zero lift and go to the other side, then you see that the vortex starts the other way, because now we have pressure above and suction below. You might think that what we see here in this pretty small, more or less two-dimensional tunnel is only a kind of a visualization, but it might not be completely true. But we have therefore made some pictures in our three-dimensional tunnel. That means a tunnel which is so wide that you can put at least half a wing in it. I think you remember I told you once that this tunnel has a rectangular cross-section, and we fasten the wing on one side, so we see half of a wing, and the vortex develops then on this wing tip. And we have made several pictures where you can see them. Here are now the films. First, a picture where we see where the smoke comes out, and we begin with no speed at all. Excuse me. The moment we blow, the moment you see that the flow which came out underneath starts around the wing tip and flows to the top and forms behind this wing a vortex. Here we have, for instance, a condition where we have no lift. Now we increase the angle of attack, and at once the rotational motion around the tip starts, and you see very distinct these particular flow lines, which now spool up all into kind of a rope, which forms this vortex, which starts from the upper part of the wing tip. We have then a picture where you can see this from above, so that you can observe that the core of the wingtip doesn't start just at the corner of the wing, but more or less at this edge where the upper surface of the wing ends, and it is a little bit set inside, so that the distance between the cores of these two wingtips is not the two span, but it is a little smaller than the span. This causes a certain loss of energy, because then the vortices are even stronger. With particular changes and particular forms of the wingtips, you try to improve this. Here we have the picture from above. But we see it even better if we can look at a film which is taken in the same tunnel just from behind, so that we observe the rotation more clearly, and then we can do it here. There it is. And we have released also some smoke from the leading edge to show you that not only the air masses which are just around the tip produce this rotational motion, but that also other masses of the air which are in between the two vortices take part in this rotation. The core of the tip vortex is in some pictures to see as a fine dark line. Actually, these vortices are very stable and stay there for a long time. So if some airplane has flown over a certain region and it has left this place, the tip vortices which he has produced will still stay there. Here is a very nice picture direct along the core of the vortex, where you see very well this rotational motion. Again, a picture from the side view where we see the single flow line, and we observe one thing, that the slope of the line increases towards the rear, because this rotation is caused by the lift. Now, the front part has not all the lift, but until you get to the rear end, you have assembled all the pressure differential which is there, and therefore the spiral gets steeper and steeper towards the rear. Now, we might think how this vortex motion ties in with what we talked before, that the air is moving downward even at the point where the aircraft flies. You see, when we have here the wing and these vortices on both sides, they induce a downward motion behind the wing. But when you see it from the side and you have here this vortex and here this vortex, this motion, this downward motion is even beginning before the wing is at this point, so that when you look at it from the side view, there is a downward motion of the air at the point where the wing is. And in this way we have to go uphill actually all the time, and the work which we need to produce lift is the work which is necessary to go in this uphill direction. Now you think, what could you do to reduce this? Well, let's think about it. We have, as we said, underneath the wing, the higher pressure, above the wing, the lower pressure. If we would distribute the load on the wing over a larger distance, a larger span, we call this distance from one tip to the other tip the span of the wing, then certainly the pressure differential across a certain section will be smaller. And therefore, when this pressure differential from below to above is smaller, then also this rotation is smaller and we get smaller tip vortices. And that is the reason why for a highly economical aircraft we should have wings which extend into large span. And since we cannot increase the surface of the wing, otherwise we would get too much surface friction, we have to have a very slender wing with a small chord, the chord length we call from the leading edge to the trailing edge, and a large span. And this ratio between the span and the mean chord of the wing, we call it the aspect ratio of the wing. You might hear it very often when people talk about it, aspect ratio. And you see that aircraft for high flight economy have high aspect ratio. All these laws of the vortex motion and the vortex formation on the wings were discovered originally by Lanchester, and the theory about this whole problem was mainly worked out by Prandtl in Göttingen. It was first applied on gliders, and I have here a picture of a high-performance glider we did a long time ago, where you see very well that we have a very small chord and a large span. Actually, this aspect ratio of this particular high-performance glider was 20:1. That means the chord, the mean chord of this wing, is 1/20 of the span. And if you look at a modern transport aircraft, at an airliner, you will see that such an airliner has again a very slender, long wing and uses the main basic principle of high flight economy in generating lift, as we did it once on the high-performance gliders. Now, you could do that, not all the time. You couldn't build a very slender wing because, well, you must think that when you fly, you have to suspend the weight. And when you build a very slender wing, then you have to have a very heavy structure within the wing to keep it from bending too much. And therefore there is a certain technical limit in having wings with high aspect ratio. And you sometimes think of methods to make this process more efficient with normal sized wings, especially if you come into the high-speed flight condition where you cannot afford to make long, slender wings at all due to other laws which are connected with the high-speed and supersonic flight. And there you see, for instance, an application which you can observe very often on jet aircraft, on high-speed aircraft, where you see that on a wing which has a normal span, we placed out there two streamlined bodies which now are used as tanks, so-called wingtip tanks, or for housing radar equipment, anything like this. This has a meaning that when you put such a rounding on the tip, then this motion around the tip will be more smooth. And you actually can, in this way, improve the flight efficiency of such aircraft. We have made a picture of such a wingtip tank on a normal wing in our tunnel, and you will see it here. Now, what we learned today is this. The formation of the wingtip vortices causes a downdraft on the wing itself, and in this way needs power to climb all the time against an air mass which is in the downward motion. This downward motion is induced direct by the aircraft itself. And therefore we need power to generate the lift. Actually, it is so that in cruising flight, 50% of the power is needed to overcome the air resistance, the friction drag and some turbulence. And 50% of the power is needed to generate the lift. In our next program, we want to talk about the development of the aircraft type of the original biplane to the latest types of aircraft as we have it, for instance, with the swept wings. As you see here, a model of it, which we just put shortly in the tunnel so that you might observe also the flow around such a wing. Now my assistants have mounted this swept wing model in the tunnel. And if I turn the light on, we can see very well the flow around such a wing, where you also see the formation of the tip vortices. But let's talk about this in our next program, where we will explain the development of the aircraft configuration from the biplane up to the latest types, the delta wings for the supersonic flight. Up to this time, goodbye and auf Wiedersehen. You know, If you would ask somebody today to sketch up an airplane of the early days of aviation, he would certainly draw up such an old biplane with all its struts and wires bracing, a real what we call the wire entanglement. And you are wondering why in these early times they went to such an effort to make such a complicated structure as their first aircraft. Now, to understand this, you should think about the condition under which they had to build these aircraft. First of all, well, the engine power was certainly not as abundant as our engine power is today. But when you think, for instance, of the Wright brothers engine, well, it had 12 horsepower, and the weight with all the things on it was almost 200 pounds. So there wasn't much power. And as you have heard in our last program, the power to fly consists of two portions. One portion is to make the aircraft go, to overcome the drag, the resistance. Another portion is necessary to make the lift. Now, you want to reduce this as much as possible. How could you probably do it? First of all, if you go very slow, then you wouldn't have much drag. So this power due to drag would be small. But if you want to go slow, then you have to have lots of area, wing area, to make lift at this low speed. So what you needed was an aircraft with large wing area, and on the other hand, since weight had to be lifted, the thing had to be very light. Now, at this time you didn't have much choice in materials. You had just wood and things like this. So you had to build a framework which was as light as possible and had as much wing area as you could think of. And in this way, the biplane was the best solution. But there was another advantage. And this advantage is that the power to make the lift is actually smaller if you divide the lift into the two surfaces instead of having it all on one surface. You remember the last program we have talked about these wingtip vortices, and then they actually extract a certain amount of energy which you have to produce with your engine. This is the energy to make the lift. Now, if you have a structure with two superimposed wings instead of one wing, then you necessarily have, instead of two wingtip vortices, you have four wingtip vortices. And the energy to generate these tip vortices is not direct proportional to their magnitude, but is proportional to the square of their magnitude. And so a simple calculation will show you that if you divide the lift on two superimposed surfaces, you actually save about 50% of the power. Look at this. We have here a monoplane wing, and we have on each side a tip vortex. Let's suppose this vortex has about the magnitude of 10. So then the energy to generate the tip vortices would be the square of 10. That means 100 here and 100 there. Makes together 200. If I take now two wings, then I have only half of the lift, on each wing. And therefore I have only half of the magnitude of the tip vortex on these wing tips. That means that each of these tip vortices on the biplane would have only the magnitude of 5. And the squares of it would give here 2 times 25, here 25, and there 25, and there 25, and there 25. This is together here 50, and there 50, and what we come out is an amount of energy which is only 100. That means half of what we have to do for the monoplane. The only problem is that due to the superposition of these two planes, you have a certain interaction so that you don't gain the full amount of 50%, but you gain about 75%. On the other hand, you have interaction from one wing surface to the other, which we probably can see much better if we look here at our model in the smoke tunnel. And I can show you how the flow acts. If I, for instance, change the angle of attack as this, or decreasing it as this, I can also change now the position of the wing above each other, what we call the stagger. You see, when I pull it forward like this, then I get what we call a positive stagger. That means the distance between the leading edges here, measured in the vertical plane, is what we call the stagger of the biplane. This is now positive stagger, and if we go backwards, then we have negative stagger. The usual biplanes had mostly positive stagger because you get more lift with such configuration. To see this more precisely, we have made some slow motion pictures of the pulsating flow in a biplane configuration, and you see here that due to the interaction of the planes, you have now 3 different general speeds. The flow above the surface of the upper wing has the highest speed. The flow between the surface has mainly the main speed, and the flow underneath the lower surface is retarded and gives higher pressure. It is therefore that the lower surface of the upper wing and the upper surface of the lower wing, due to the interaction of the pressure in the channel between the wings, has not much action. Some pictures can be seen here with different type of stagger, and you see that the main configuration of the velocities is almost the same. The change is not very considerable. Now, if from all these considerations the biplane was such a good design, why did we then change to the monoplane? Well, there were 2 main reasons. First of all, after the First World War, where the airplane was mainly used for military purposes, engineers began to think about the use of the airplane as a means of transportation. Now, if you do this, then you think that you have to have some kind of economy of transportation, which means that you have to have low fuel consumption over a certain distance. Fuel consumption per distance counts for economy, as it is on your car, where you think of gallons per mile. So you had to fly faster to get higher economy so that you could fly with the same amount of fuel over a larger distance. And then you had to reduce the drag first. Now, to reduce the drag, you needed to take off all this crap, all the struts, wiring, and all the external things which were built on these old biplanes. What could you do? Well, let's think of it. Could do it probably this way. You could have here your biplane, and you could think, all right, if I take these both surfaces and put them all together so that I get one thick surface put together from two, and then I can take these outer members and bring them in here. And so I would have a structure which would contain all members to make the thing stiff inside of the wing, and I would have a very smooth outer surface. So instead of having this conception of thin wings with struts in between and lots of wires, you have a thick section with a spar which now contains these struts and cross members inside of the wing. You just have reduced the height of this configuration. The first people to think about such thing were the Germans, I think, and it was Hugo Junkers who, in his wind tunnel in Aachen, tested the first 6 wing sections. And it was, on the other hand, the famous designer of the World War I fighters, Anthony Fokker, who used this research work for building the first 6-wing commercial monoplanes. Actually, this development, which began towards the end of the First World War, did not come into use, really, generally speaking, until one event showed that the aircraft was grown out of his childhood. And this was the crossing of the Atlantic by Charles Lindbergh, where it was shown to everybody that now the aircraft was a large range means of transportation, and crossing the oceans, going over thousands of miles, could make the aircraft as a usable mean for all kinds of civilian purposes. The question was again to improve this by reducing the drag. Now there was another idea of reducing the drag. We took all the outer structure away. Well, what was left was apparently the fuselage. If we had anyhow a thick wing section and we could build a large wing with a thick section, couldn't we probably place all the passengers, the engines, the fuel tanks, and probably the undercarriage into this thick wing and make a flying wing, an ideal aircraft which would not have any outer structure and all lifting surface only? Well, also this idea, which originates with Hugo Junkers, is actually quite old. The patent is from 1913. But it did take quite some time until we were able to think of a design which would make it possible to design such an aircraft. Because now, since you take the fuselage away, well, then you have to have the tail units, the elevator and the rudder on the wing itself. Otherwise you could not control the wing. So you have to have a wing for lifting and a wing for controlling. This could be done. And I will show you here a little model where I will perform this change of a conventional aircraft into an all-wing aircraft, while you may look to it. See, this is normal little model, and we can fly it very nicely. I fly it probably over there. You see, it flies pretty nice. So, now, what could we do to get rid of all this? We have to put, apparently, the tail units on the wing. So, all right. Let's take this off and make first a swept-back wing. A wing which goes arrow-like to the rear, which is outer surface. Excuse me, I have to take my eyes, you know. So now I put this little triangle here in front, so that we have a real swept-back wing. Now we take the tail unit off, and we take part of the fuselage off because we don't need it anymore. And then we divide this into two and put this one on the right-hand side on the left-hand wing, and the left-hand side on the right-hand wing, and attach it there. Because due to the swept back, we have now a leverage for these control or stabilization surfaces. And if I am a little able to do that, you see, then I attach these surfaces now to the wing tip. So, and we have now an all-wing aircraft. And you will see that this flies very well. I can even take a little weight off. Now, and there it goes. You see, we have, in this way, found a mean to build an all-wing aircraft with swept-back wing. Now, after all this refinement of the monoplane configuration, the way was free to build a very nice and efficient airplane. And so we went from 200 miles up to 300 miles, and with some more refinements and some better engines, we got from 300 miles to 400 miles, and then from 400 miles to 500 miles. And suddenly, you know, there was somebody who told us, well, that if we would proceed and get into the range of 700 miles, there at 770 miles per hour, there would be a critical speed, the speed of sound. And some mathematicians, theoretical people, aerodynamicists, well, they figured out with big equations, you know, that in this range, beyond the speed of sound, all our original conception of laws of fluid motion would change considerably, and there would be completely different conditions for the flow in the supersonic range. So we should begin from scratch and learn new type of designs for the supersonic aircraft. Well, this was too bad, you know. When you face such a problem and you think to get this transition from subsonic to supersonic, you search for some means of delaying this sudden change and of having something which at least would it make it possible for you to extend this transition over a certain range. And again, it was the theory, you know, who predicted very well that if we would use, instead of the straight wings, the swept-back wings on such high-speed aircraft, we would be able to enter into the so-called transonic and supersonic range with the otherwise normal aircraft configuration. In this way, we achieved transonic and supersonic speeds. But you know, it's very well to fly with a Mach number of 2 and 3. But there's one thing, you can't get home with it. Oh no, you have to get home with 0 speed, and you have to get home with a Mach number of 0. And therefore, our problem was not only to produce a high-speed aircraft, but to make an aircraft configuration which also had a certain amount of good properties for takeoff and landing. And to show you some of these high-speed wing configurations with swept-back in the low-speed range and their special flow characteristics, we have here in our tunnel one of those models where you can see the low-speed flow configuration on a high-speed aircraft wing. And we can see how the flow works in the low-speed range on this model. With these control wheels, I can change the angle of attack, and when I now increase the angle, as you see it now, then you see a very distinct change in the flow. When you think of the straight wing, the flow went straight over it. Here, due to the swept-back, we have a convergence towards the center, and the flow is more narrow behind it than it is in front. On the other hand, we have again 2 pretty distinct tip vortices on the tips of the wing. It comes out that such swept wing configuration is not very efficient. To make it even better for the very high speed, you had to sweep the wings more back. And what you come out with is then that if you take such a large swept back like this, you better connect the both wing tips together and fill this part out and make a triangular wing, which we call the delta wing, and which I, fortunately or unfortunately, you don't know, tested for the first time. This is one of the old models which I designed in '44. We have now, to observe some of the flow conditions of the delta wing, we have made some tests on flow pictures which we show you now here, and which are taken from a flying model with smoke on it, so that you can see how these large tip vortices develop now along the whole leading edge. Actually, what this delta wing represents is just a wing which is put together from 2 wing tips. We flew this in a hangar, and the smoke is produced by a smoke generator on the model itself and comes out through holes on the upper surface. If you make the wing a little bit thicker, then you would have a delta wing with a thick wing section as you see it here in the smoke tunnel. And you can observe very well the large convergence of the flow lines when the thing comes to a larger angle of attack. To see this more distinct, we have pictures from our 3D tunnel where we have a thin delta wing model, and you see here the flow when we change the angle of attack from a 0 angle to a larger angle. You can see very well the two wingtip vortices which are on the leading edges of this wing. On our next program, we will talk about all kinds of high lift devices. And to show you some example of a very high lift wing, I have here a special wing, which is just nothing than a circular cylinder. And if I rotate this and fly it forward, then the circulation around it and the translation causes very high lift. This is called a rotor, and you might see it fly here. Now watch this. You see, it flies beautiful and with very low speed. We will talk about other types of high lift devices and of the system to make what we call today super circulation. Goodbye and auf Wiedersehen. In our last program, I have shown you this flying stick, the rotor. And I think it might be nice to show it to you again now and fly it again here in our studio. You see, this line we have wound around, this gives this rotor a rotation this way around. That means it rotates as if it would roll on a surface above, just opposite to a wheel which would roll on the ground. And you see, when I let it go, it flies now very nicely. How does this happen? And how does this come so? Well, let's think about it. We have a circular cylinder. And when we rotate the circular cylinder, then the air which is around the cylinder will also begin to rotate, so that we have what we call a circulation around this cylinder. Now, if we move this thing forward, then this rotational motion, in this way now, move it forward, this rotational motion would add to the forward motion. And since we have here, for instance, the cylinder which goes above due to its rotational motion above this way and underneath this way, the forward velocity against the cylinder would add here to the velocity on the upper surface and underneath diminish this velocity, so that we have a difference in speed above and below. Now, if you remember, when the speed increases, the pressure decreases. When the speed decreases, the pressure increases. So, up there we have more speed than average. Down there we have less speed than average, and this gives us up there lower pressure, suction, down there more pressure and the swing is resultant as a lift force. And the flow which we have here, if we would think that we would have no friction in the fluid, would look like this. And go over here and produce a lift normal to the flow direction before this thing hits the rotating cylinder. Now I can show you the same thing in our smoke tunnel. And we have here a cylinder in it. And when we make the flow lines and then begin to turn the cylinder, which now runs, the flow comes from this side, runs around this way, then you will see that at once an asymmetrical flow field develops, which you see, come on, run it now, where you see that the velocity above is higher, the lines are more narrow, and the velocity below is lower, and the lines will be wider. Now we will begin to rotate this. I will go out of the flow field so that you can see it. Now we have the cylinder in the tunnel and we begin to rotate. Look at it. The more we have rotation, the more flow lines are pulled over the upper surface of the cylinder, and you see at once that our speed is very high above and quite low underneath of the cylinder, which gives us a lift normal to the direction of the flow. Now, you might ask me, what has this to do with a wing? What has it to do with the lift of a wing? This is no wing, and we cannot fly with such a rotor. Or we will have quite a bit of drag, because you see here this much wake behind the cylinder, which necessarily indicates that there's lots of drag. Well, the main point which we have here is this, that when we have circulation and translation, translation means here a straight motion, a straight continuous forward motion. When we have circulation and translation, then we will have lift. And the interesting thing is this, that a wing produces this circulation without such gadgetry as we use it here, first to rotate the cylinder. The wing, which has a very special shape because it's round in front and sharp at the rear. This wing, due to this sharp corner, develops a flow which you, as well as we did it on the cylinder, can take apart into a circulating flow around the wing and a translation which gives you then finally the flow picture which shows you the lift of the wing. So actually the lift of the wing is in the same way developed as we develop the lift on the rotating cylinder. Now look at the wing here in the tunnel and see when I change the angle of attack of this wing, then I increase the lift in the same way as we would rotate more and more the cylinder. But you know, this has certain difficulties, because to increase the lift only by changing the angle of attack of the wing would mean that you have to change the whole attitude of your aircraft. So if you want to fly slow, which you necessarily need in takeoff and landing, well, then you had to tilt up your plane quite a bit to get this higher lift. And especially if you have passengers in an airliner, or you have other kinds of freight or something in your fuselage, you wouldn't like to change this attitude so much. You are much better off if you could fly your fuselage straight and still change your lift. How you do it? Now you change parts of the wing in angle of attack. You change only the rear part and give him a larger angle. And this is what you see here. See, when you make a flap back there, as we did it here on this model, then you will see at once that if I change the angle of the flap, we also change the lift and have the same effect. You see it here? You see that the moment I change the flap, the moment the more streamlines go over the wing. That means the higher is our circulation. Look at it once again. There we are. There we are. And you see, a flap therefore acts in the same way as the change of angle of attack. Now, you see, as long as we have that wing in this position, this increasing the lift with the flap is all right. But it might sometimes happen, you know, that you have your airplane in a different condition, and you might have it even pulled up. So it might sit something like this, which is not too far from the stall. When you now use your flap, what happens then? Then the airfoil doesn't take it anymore, and the wing as such stalls out, which is quite dangerous, especially if this flap, for instance, is on the outer part of the wing, and you put one flap down and the other one up, and then this one, which you want to get up, stalls out and comes down, and, well, you know what happens then, huh? You call it timber. Anyhow, how can we change this? Or what can we do to prevent the stall under such conditions? Now, two fellows, Sir Henry Page and Dr. Lackman, they got this idea during the First War, and the thing is this. You see, when I have it in this position and I put the flap down, the flow cannot follow anymore this upper curvature. We have this wing here, and the flow cannot go around here and stalls away. And this is a dead air zone. Now, to prevent this, what could we do? We could probably make a slot into the wing and let some of the air from underneath go into this dead air zone and blow it away. And we actually have a model of this type here. See, a model where we have what we call a slot on the nose. And I can operate the slot in this tunnel. And then you will see that we can prevent the stall with it. Now, this method of having a slotted wing is not only used for preventing the stall on the nose, where it's now, as you see it on fighter wings, for instance, used to prevent the stall when you make a tight turn and you have a kind of an automatic slot which kicks out when you have this high angle and prevents the stall. But you have also wings where several slots are one behind each other. And remember what you have seen in nature. A bird has this in its outer so-called primary feathers. And he prevents the stall with the same method than we have it here today on the airplane. Now we have this model in the tunnel, and let me demonstrate to you how such a slot actually works. Let's first put it into a position where when we deflect the flap, the thing stalls out. Now if I move out the slot, then you see at once that part of the air is vented into the upper surface and prevents the stalling of the wing. See it? Here, once more. Now you can make this going automatically, and in this way you can even prevent any dangerous situation even if the pilot is not able to think about it. But the trouble with the slotted wing is this, that due to all this machinery which you need, you have quite a bit of drag on it, and it causes more drag than a smooth wing, which is obvious. So people have looked for some other means of making high lift, especially since we have developed into a stage of aircraft designs which now reaches into such high speeds that our true difficulties are in the low speed range, where these high-speed aircraft still have landing speeds which are way above 100 miles per hour, and you need long runways and big installations to make the thing going up and coming down. Could you do something about this? Then you should do first some kind of artificial lift. Now think what happens here with this stall. When you think about it, as I showed you, this flow disattaches from the upper surface. So how could you bring it back? Well, you could bring it back probably in taking this air, which has lost its energy, which has lost its momentum, take it away. Make some little slots in the surface and put suction into the wing and suck the dead air zone away. And then it would stay attached. This air zone, which is here between the wing and the surface, as you know, we call the boundary layer. The layer which is in the boundary between the wing itself and the outer air. We suck part of this boundary layer away, and in this way achieve a very high lift. I have here a model in this tunnel which has little slots on its surface, actually several ones. Here one in front, the next. These are 5 different slots, and you will see that when we now first give it a large angle of attack so that it stalls, and we put suction on it, then it reattaches and we can go to very high angles of attack to prevent the stall, as you see it here. You see, now I can go quite a bit up with this wing until it stalls. And when I do this boundary layer suction very slowly in the normal range where we want to fly with high speed, then I even reduce the drag with it, because the dead air, which has lost its momentum, will now be sucked in and accelerated through the blower system. This has advantages, many advantages, and was, well, proposed long time ago. Actually, it was one of the first products of the boundary layer theory, which was founded by Ludwig Prandtl in 1905. So 50 years ago, this system was proposed and is not as yet in use. Why? Because in the meantime, where we really need to apply it now with the high-speed aircraft, the wings got so small that there is no space inside anymore for putting these large ducts in it to suck this boundary layer away. Because when you suck, well, then you need a large duct, because this air which you suck in will have low pressure and a large volume. So, is there probably something else to do? And is there probably another method which would be, from the standpoint of design of aircraft, from the standpoint of engineering, easier to be used? Well, there is. And this is just the opposite to this boundary layer suction. It's blowing, because, see, you could also accelerate this dead air zone, this mass of air which has lost its momentum on the surface. If you would blow to it, well, then you would get almost the same effect. And let's look at another model which has now a blowing slot on the surface. Now we have a section in the tunnel which has on the upper surface one slot where we blow out the air over the upper surface so that we can now accelerate the boundary layer and in this way get it attached, reattached. You see, I start it now, and when we now blow, you will see that it reattaches. It actually, at this point, it's really a little bit too much blowing. But you see that at once we have a very large lift. Now you can see this even better if you look at a slow motion film with pulsating smoke, which we have here. And there you see at once how fast the flow moves over the upper surface. And as you remember, the difference between the smoke lines on the upper surface and the lower surface is a measure for the circulation. And you see here how much circulation we have with this blowing slot. Now you see this blowing has the advantage that you can lead the air to the blowing slots through small lines, and in this way it saves space and has a much more practical application. Now you don't need the blowing just for making high lift, but you can also make kind of an invisible flap by blowing out at the rear end of the section. That's what they now call a jet flap, a section where here is the tube in it and we blow out this way. And this layer of air then works like a jet flap, as you see it here. You see now we have at the end of this section, we have a tube and we blow out of the tube, and in this way we increase the lift and we also can control the lift of this section all over. Now if you go farther, you would think of using such systems in many ways and making a body which makes now the lift in the way as we originally thought about it. So what could you do, for instance? You think we had first the rotating cylinder, completely round. Now you wouldn't fly with such a thing. But probably you could do this. You could take a more elliptical cross-section and make this big thing, which is easy to build, lift. What you would do then, you would blow out air over the upper surface and probably at the rear to make the circulation going and achieve in this way a configuration which gives very high lift, and this high lift with a cross-section which is easy to be built and constructed. We have such a section which we call a super circulation section, an artificial circulation section in this tunnel, and I will show you how it works. Now if we turn the smoke on, we will see the flow as it is without blowing. Now you see this flow with this super circulation. We have almost achieved the picture which was once predicted by the theory, where we have here and there a stagnation point, very low speed underneath and very high speed above. We can do that artificially with blowing over the surface. We have also a high-speed film of this, and we can look at it and see how the timelines are now quite wide from each other, and we can see the large amount of lift which we can achieve with such a section. In our next program, we will talk about something really interesting, and I will just show you a little experiment which might make you thinking. See, first I light a candle. Now it goes. I put it here somewhere. So, and now somebody wants to blow the candle out. I don't need to go there. And there you are. Now what is it? What I shoot there through the air? It is a vortex. And you might even see it here with this little gadget where we have smoke in it. And when you look at it, then you see that there are all vortices coming out of this. Well, this is the smoke ring, as you know, is used very often for demonstration, and which actually is one of the main examples of a vortex. And when we think about what we saw today, that circulation around the wing is in some way nothing than making a vortex which is now bound to the wing and with the translation makes the lift. The main thing is this, that a vortex behaves in air as if it would be a solid body. We will look at many applications at our next program. Goodbye and auf Wiedersehen. When I explained to you in one of our last programs the generation of lift as a superposition of a rotational motion around the wing and the straight flow, we call it the translation, then you might have thought that these fabulous lift forces which carry these large airplanes with several hundred thousands of pounds through the sky, that these lift forces are in some way generated by a vortex motion, and that this vortex motion is necessary to make the lift of an airplane. Well, there are many other cases of such rotational motion in the fluid. And since the vortex is so important in many cases of fluid motion, let's talk a little bit about this strange fellow. Well, the last time, I think I showed you some ring vortices out of this box. And, well, since it is so nice, let's make some more of these. I think you see it better when I stand here and shoot it across our tunnel. Let's see. Now you see them? They go straight out. And it looks to you there as if you shoot just air through air. And when you look at them, you observe at once one very important law of vortex motion. See, the smoke comes out like a bullet. That means that all the particles of air which contain the smoke, or which are smoky air, stay together in this ring, which actually is nothing than a vortex ring. That means we know at once that if fluid is bound in a vortex, it stays together and goes through the other fluid as if it would be a solid body. On the other hand, when you look at this close, then you see that this rotation around a vortex is different than the rotation of a wheel. On a wheel, the outer peripheral parts move faster than the center. On the vortex, it's just opposite. The center moves fast and the outer moves slower. Now, how do we produce this? Well, let's think about it. Let's have a cross-section of this thing. This is a box, and there we have the bottom with a hole in it, which has very sharp corners. Now, we punch against this membrane, which we have back there, and then we produce a pressure wave which goes through here, hits these corners, and blows out a bubble of air, and then a bubble of air comes out here. This takes little particles which just were sitting here with it, and then new air has to flow towards the point where you have taken away these particles. So this motion and this motion produces a spiral motion which makes a kind of a mushroom, and out of the mushroom finally comes your ring vortex. We have made some high-speed pictures, some slow-motion movies of this generation of the vortices. And let's now look at these pictures. First, we see a front view of the box. And it's very interesting to observe first the radial motion of the air, and then the bubble is formed and comes out as a ring vortex. In the next picture, we see the same process from the side. And since we have a membrane back there which is elastic, the bubble jumps in and out first before it finally travels away as a ring vortex. Here we have another tube where we have another kind of a membrane on it, so this doesn't happen, and it looks like an atomic explosion, actually. But the most interesting view is to see it from in front, which is this picture again, and observe the vortex formation before it comes out. This is most interesting, and I think it's only shown in this high-speed picture. You never can observe it with the bare eye. Now, what we have seen here was that the formation depends on a flow across a sharp edge. And behind the sharp edge, the vortex is forming. Then we remember that we saw this once on an inclined plate. Actually, the formation of the wingtip vortex is nothing else than it hits the sharp edge of the wingtip, and then the flow rolls over it and forms this wingtip vortex. Let's look at this thing again in our smoke tunnel. And we have, in this case, we have just a part, the ending of a flat plate in it, and when we turn the blower on and we have some smoke, then we can very well see again the formation of this spiral vortex from this corner, where the flow actually stalls away and new air from the side moves in and forms then this spiral motion. You see it here very well. And when you look at it from the side, then you can actually see the three-dimensional development of this spiral motion. Now, you know, we have made these vortex rings and the straight vortices in the air. And you might think, can you do that also in other fluids, for instance in water? Well, I will show you. You can actually do the smoke rings in water, and we have here a water tank. We don't have fishes in it, but we have a hole at the center, and underneath of this tank we have a little container with colored water. We have some ink in it, and with a membrane underneath. And when I push this membrane, then we make the same smoke rings here, the water rings, as we did it in air. Now watch this. See, I push it up and let it go slightly. And there's the smoking. Do you see him? Another one. Another one. When I make it a little bit more violent, then you see that it even jumps out of the water. What's this? Oh, this. Now we don't want to color this all up, because then we don't see our rings anymore. But I will just make one more. You see? Therefore, we can make these vortices also in such a dense fluid as the water is. Now, when you look at the rings and you see that they jump out of the water, at least at the center, you think about what sense of rotation is in there. Let's talk about this for a moment. See, we have actually here our bottom, and there's a hole in it. And now when we push, then the water comes out of it, and as I told you, forms first a bubble, like this, a mushroom, and out of the mushroom comes finally this ring, which travels up there as a true vortex ring. The center of the vortex is somewhere here, and the highest motion is in the center. Now the sense of rotation will be then this. Since we push this way, we have a rotation which goes around this way and this way. That means the outer turns back and the inner goes up. And when we now hit the water surface with such a ring where the rotation is this way, then we have a water column which now jumps out of the water here. Since we have in this center, we have the velocity against the water level, and the other ring disperses along the water surface. Now, you have probably yourself observed in water another type of a vortex. You know, when you open the sink of the bathtub, let the water out, you often observe that there is forming a kind of a funnel, and that the water begins to rotate and form such a funnel of air and surrounded by rotating water particles, which actually forms a straight vortex going into the sink. I think we can show that also here in our water tank. When we let it out, then first, due to discontinuous motion, due to some disturbances which are in there, the water which all wants to flow towards the center misses this center a little bit, and due to this, a rotation begins which finally forms this funnel. Now it slowly begins. You have to wait a little bit, and this depends on the level of the water when this vortex actually develops and the size of the opening. I can see from here now that the rotation begins to form. And pretty soon you will see that due to the low pressure, which is in the center of the vortex, there will develop a little dip in the water, which shows us the beginning of the vortex formation, as it is now. Now you see it beginning, and then it pulls down. You see it now coming down and going towards the outlet. See now? And this gets stronger and stronger. You get a little wet with these experiments, but don't bother. And you can see now this vortex funnel very clear going down into the sink. The rotation in the center is quite strong. Well, let me explain to you a little bit more how this comes to such a rotation. And while it runs out, well, we can see a little bit still. We will talk about the cause of such a vortex. The main thing is that you have to have a sink. That means what is first with the formation of the vortex? What is first, the chicken or the egg? And what is here the egg and what is here the chicken? Well, the chicken is the vortex, and the egg is a low pressure area where everything flows to it. Now, when it does this, when we have this hole in the center, we pull the plug out, then all the water wants to go towards the center, because the pressure here is lower than the pressure in the surrounding water. Since we pulled the plug, at this point, we have no water pressure from above. Now, theoretically, these lines and these flow lines should all come into the center. but due to little disturbances which are on the floor and which are in the water anyhow, some of the particles will not have the straight line into the center, but just miss it a tiny bit. Now, when one of these lines misses this point and shoots over here, well, then it is sucked back into it, and so this rotation starts. And then, since this missed it, the other particle which wanted to go here comes also around and does the same thing. And then finally all of them do this, and there we have the vortex. Due to the courtesy of the Hydraulics Research Institute at the State University of Iowa, we have some nice films of such vortex formation, and we can see them here, especially a film which is taken from above, where you look to the vortex formation from above, and you see very well in these films the velocity distribution in the vortex. You see where the center rotates the most, and towards the outer, the rotational velocity gets smaller and smaller. Now we see here again the development of the funnel from the side view. First, a very fine line which gets wider and wider when the rotation increases, here due to the gravitational forces which push the water out through the bottom sink. And finally, we have a big funnel with a very strong rotation around the center. The low pressure at the center is so low that we have, instead of water, we have here air in it, because the water level itself goes down up into the sink. Now we have put some dye into the funnel, and you might see the flow around the funnel itself made visible by putting some dye into the fluid. There's a picture where we see the outer motion of the fluid. If you see these experiments with the water funnel, you might remember that you have seen this too in pictures, or even if you are from the south, in nature, as a big tornado funnel. And you might think that there is some striking similarity between the funnel of the tornado and this outlet vortex in a water vessel. I think before we talk about this more closely, let's look at some of the pictures which we got about the tornadoes, where we can see them and observe their formation. Now, besides of this most violent of all windstorms, the tornado, which represents a vertical vortex column, we can observe in nature also horizontal formation of vortices. And I have here an experiment built up where we can see a special vortex formation due to the fact that we have a hot plate underneath on the bottom and a very cold one on top. And when we let the flow go through this channel, then due to the convective motion, the hot plate heats the air on the bottom, the thing goes up, the air goes up, hits the cold layer on top and returns again. And you see in this a row of counter-rotating vortices. Let me explain just shortly this little apparatus. We have here a box here with a glass wall on top, here on the side, where we can look into the channel. There is the channel itself. On the top we have a metal plate with dry ice on it, so that's real cold. From underneath we light it and have a glass wall, so the light comes on the glass wall and heats the glass wall, so that the glass wall is hot. And then we suck this off by a blower. When we turn on the blower, then we can see this little noise, huh? Smoke develops. We have to look then into this thing from here. And when we look this way in, then we can see a picture which looks almost like this. There we have the hot plate. It's hot, that's cold, and there we have counter-rotating vortices. So the air goes here up, there down, here up, and there down. If we have this in nature, where the air goes up, clouds are forming, and we see long, mile-long cloud streets forming when we have cold air on top, a very cold layer on top, and the ground is heated by the sunshine. The energy which makes all these vortices comes in this case from the heat, and in the atmosphere also due to the layers with different pressure and density. You can observe also a vertical vortex forming from the ground, which we call the dust devil. And we have here a small glass box where we can make little models of such dust devils developing from the warmer surface of this box. It is enclosed so that we actually can see better how these vertical vortices, these dust devils, develop. The main thing is that we have a very warm layer on the surface itself, and when it rolls over, due to the slow motion, it begins to roll, and then a vertical vortex spools out of it, as you see it very well in this box. The warm layer is what we see here as a smoke, and all these spooling up lines are actually vortices which are produced from this warm air going up and rotating as it goes up, because the air can only go through other air if it assembles into a vortex. And you see here very well that every of these fine lines is actually a vortex. Now you see it very near to the formation and very near with the camera, and we can observe more distinct this rotational motion. But let's get back to our aerodynamics. We get too deep into meteorology. A vortex which we saw was the wingtip vortex. And here's a picture of a cross-section of such a vortex which we took in the 3D tunnel. Isn't this a striking similarity to something which you might have seen sometimes in pictures from the great telescopes which survey our stars in the sky. When you look at the picture of the wingtip vortex formation, and you see a picture of a galaxy, of a spiral nebula, you see that something is similar in both pictures. I don't know what it is, and I doubt that we have a clear explanation of this similarity and whether there is any spiral motion in the sense as we observed it here. But you sit here on such instruments and apparatus and see these strange things develop, and you think it over, and you finally end up that anyhow many things stay unexplained to you. As the great poet says, mysterious even in the light of day, may never nature of her veil be freed, unless she willingly unveils to you nothing you thought from her, with lever or with spoon. Goodbye, and auf Wiedersehen. Come on, come on, come on, come on, come on. There it is. You see a mechanical bird. And, well, when you look at it, the basic system of flying is here the same system as the bird has it. The inner part of the wing gives a lift, and the outer part of the wing propels this little aircraft model. Now, to explain it a little bit more to you, you see there is a crank shaft in there, and with two connecting rods, we move the wings. See, when I now wind it up, I just push one of the connecting rods, and then the wings go up and down. So, and when I have wound up enough of these two rubber bands, here's one, and there's another one, this is a motor, then I can let it go. It's a little tricky, you know. And the bearings are all made from small glass beads, so they have practically no friction. You see? Now I can let it go, and it flies nicely around like a tamed bird. Well, here it is. Now, before we go further into thinking about bird flight, let's explain at first how ever a flapping motion of the wings, as it is all done by the flying animals, how this can produce propulsion and lift. Now, as you see it here in a very simplified form, the wing goes just straight up and down. And while it moves forward, this up and down motion and the forward motion will give a kind of a wave trajectory, what you call a sinusoidal curve. Let's have it here on the blackboard. So, let's begin with the wing in the upper position. This might be our center line, and here we have the wing in the upper position, and then the wing goes down to here. This is a downstroke. And from here back to the position as we began there, this is the upstroke. What happens? While this wing beats down and goes forward, the air will blow from underneath towards the wing. And when we think that we have here somewhere our wing section, then the blow comes from underneath and gives us a force which is in this direction, so that we have lift and forward thrust. Now here we have the condition as we have it normally on any wing, stiff wing, just the flow coming from in front, and we have a little drag and we have medium lift. Now when we pull it up, then in this position the wind which the wing feels comes from above, and we have actually on such a model we have a little down lift, or practically no lift at all and only a small drag, so that during the downstroke we produce high lift and forward thrust. During the upstroke, the trick is to move the wing in such a way that we don't have much drag and still maintain a certain amount of lift. Now, this is done with the bird in such a way that its center part of the wing doesn't move much up and down. This is a lifting part, while the upper parts, the outer parts, they have a much larger motion and they work as propulsion. And in this way, this model represents the same system as you have it on a flying bird. The center part gives the lift and the outer part produces the thrust. I will just hold it while it flaps up and down. You see one other thing, very clear. It is necessary that this outer wing twists, because while it goes down, the downward motion on the tip is much faster than on the hinge point, where there is practically no downward motion. Therefore, the wing, while it goes down, has to twist like a propeller twists. And you must think that this beating down is a part of a motion around a center point, and our propeller is in some way comparable with the outer part of the bird or the insect wing, because there he does the same thing, but he cannot do it all around. So he has to reverse the motion and beat back, and while he beats back at insects, he also gets propulsion. With birds, he pulls it back more in a way so that there is practically no drag with this wing because he folds it in. Now, this is one aspect of the flight. And therefore, when you think that this simple up and down motion has this difficulty that this upstroke is quite long, and you would have a long time drag in it. You could do it easier in moving the wing not just up and down, but moving it a little bit in a circular motion. Then you would change this in such a way that you have a longer downstroke and a short upstroke. And while you have the downstroke, you have all the velocity which is needed to make the lift and forward thrust. In the upstroke, you have practically no speed because you pull the wing backwards. And in this way, this wing is brought into its working position in the downstroke by the most efficient way and the way where the drag is the smallest. This method of rotating the wing we see on all flying animals, as well on the insects as on the birds. We have here a small model of a, well, bird, or what you might call it, in this tunnel. And by some tricky mechanics, we have made the wings flappable, so that with a little motor, as you see it now, we can oscillate the wings with a pretty high frequency and observe now the action of these flapping wings on the flow around the model. We can even see it better if we have a high-speed picture which we made from this model. These are extremely interesting pictures. You see, since we oscillate the wings, the flow behind this birdie is also pulsating. And we see that while it beats down, every time a tip vortex is generated. While when we would have steady wings, then this tip vortex is a steady vortex. But here we have a row of single vortices emerging from the tips of the wings. Now, if you investigate the flight in nature and observe the different types of flying animals, like the insects, the flying fish, the birds, and even some flying mammals, you might wonder why there is a difference in the texture of the wings, and why, for instance, at small animals like the insects, the wings are designed and built in a different way than it is, for instance, with a big bird. This is important to know, and it is mainly due to the fact that the resistance, the friction on surfaces at different sizes and speeds follow a different law. This can be compared if you think about what we call the Reynolds number of this flow condition, which is just a comparative number to see whether certain flow which you have investigated here, and you would again investigate here, whether this is made under similar condition. And this similarity law tells you on the other side what type of a friction on this surface you would have. Now we have here a chart, and there we have plotted these laws as they are physically and theoretically established. And we find this, that there are two different types of friction on the surface. One friction, which we call the laminar friction, where the air goes smooth over the surface in parallel layers. And another friction, which we call the turbulent friction, where the air breaks up, as we have seen it, you remember in the program where I showed you something about the drag on wings. Now, the laminar friction follows a line in this diagram like this one. The turbulent friction follows another line, which goes out here. And you see one important point, that in this range, at very low Reynolds numbers, that means at very small speeds and very small lengths or sizes, the turbulent friction is lower than the laminar friction. And above this point, the laminar friction is much lower than the turbulent friction. Therefore, if you want to make an efficient flying object in the small size, you have to make it so that it is producing turbulent friction on the surfaces. And if you have it in larger sizes, then you have to reverse it. And you have to make it smooth so you get as much laminar friction as possible. Therefore, when you look at an insect, you are always wondering why it has so many hairs on it and is so rough. It is rough because it has to be rough, since in this size, the viscosity of the air has a much stronger influence. And if you would think you have to move in something quite viscous, well, then you have to paddle around so that you get the stuff moving, otherwise you wouldn't get through that sticky stuff. And this is what this little insect actually feels, and therefore he makes it rough. While when you are way up there, as the birds are, especially the larger birds, well, then you have to be as smooth as our airplanes have to be. Therefore, if you investigate all these things, you have to understand it. And you have to see one thing, for instance, that if you take such an insect as a model of something which you want to build in larger sizes, then you have to be careful, because you could not just take this dragonfly, for instance, and enlarge it 10 times and then fly it. It wouldn't fly, because he is then your model in a complete different region of Reynolds number than your original was, and therefore different laws of friction govern this motion of the air around this wing or the body. Now let's look at some of our wonderful pictures which we have from insect flight. First, we see some silhouettes of hovering bees and flies and wasps, which was given to us due to the courtesy of Professor Chadwick of the University of Illinois. Here you see, for instance, a bee flying, and since we mainly observe here the hovering flight condition, we see that this little animal moves its wings more or less in a horizontal plane forward and backward, so that the propulsion which is now done by the wings works like a propeller, which you now put forward and backward instead running it around. You just change the pitch from the positive to the negative part and move the wing forward and backward, and in this way you get the same lift as you would give it, for instance, on a helicopter. There is a wasp flying, and you see the interesting attitude of its rear body, which is this part which is stretched out so high. So he stabilizes the flight with this tail. This is now the dragonfly, which is one of our best flyers. All these pictures now are taken from animals which are pinned to some little stick, or what you might think. And in this way, what you observe here is not quite a free flight condition, but you still be able to see how he moves the wings. And when you observe it right and clearly, then you see that these wings are not moving just straight up and down, but they are moving mainly from a position of rear up to front down. Now we have another very interesting insect film, which is the flight motion on the wings of a drone fly, which was given to us by the Sperry Gyroscope Company, who was interested to see not only the motion of the wings, but especially to see what a small little, what I would say stick would do, which this animal has behind the wings, to keep its equilibrium. It is thought that this small object, which we call a halter, would work as a gyro works, since when you oscillate a weight on an elastic stick, then this oscillating stick would give to its base the same signals, the same moments and forces as you would get it from a gyro. And in this way, the fly stabilizes its flight. Now there you see a close-up. The front is the wing, and at the rear we see now the head of the halter, which is a word which is not a halter, but means a leaping weight. And behind the wing, in a groove, we see that this little object is moving up and down in a phase shift between this and the wing itself, but actually at the same frequency. When we now come to the pictures of bird flight, we first have to remember that there is a large step from the sizes of the insect to the size of the bird, as we saw it in this diagram. And what we have to observe mainly is that the motion of the wings resembles in some way, you could say, a swimming motion in the air, where the outer portions of the wings are rotated in a cone surface. Now, to see this probably a little bit clearer, we have there a model in the wind tunnel where we can simulate a rotating motion of a wing section. Now watch this. Here we have it. And you see when we rotate it, then while the thing goes around, it adjusts itself to the local flow condition. We see it much better if we look at a slow motion picture, which we have here. Here we have the wing in the upward position, and begin with a downstroke. We see that it produces quite a bit of lift, since the flow lines are deflected. Now while it goes back, it loses speed because it has not much speed against the flow, and while it moves upward, it's only adjusted so that it makes as few drag as possible. And again, the downstroke begins with a large lift. Now, to see the bird flight, it is necessary that you make the pictures with a slow motion camera, and that is what we see here, where several of the pictures are taken with about 64 frames per second and the other ones with about 130 frames per second. So all the time our motion is slowed down. Here we see a takeoff of a duck, which needs quite a bit of run along the water to get off with this heavy wing loading as the duck has. Observe the rotating motion of the wing tips. This one is a landing, and you see one thing. The bird can do not only forward cruising flight, but it can also do with its wings a stationary flight. That means hovering. This is a big difference between the wing of the bird and the wing of our airplanes, which cannot do this. And the bird, that means the nature, has solved this problem in the most elegant way. There we see some geese, and observe how they take off just from the spot where they sit. They are real VTO aircraft, I would say. Now we have some pictures of the gulls, which are one of the most elegant flyers in nature. You see one thing, these seabirds have a much higher aspect ratio. That means they have a narrow wing and a large span. First of all, there are no obstacles like the trees and bushes as it is on the country. They fly out on the ocean. On the other hand, they use quite a bit of soaring flight where a high aspect ratio is necessary. Here are some pictures of gannets, which are also very good flyers. They partly soar and partly we see them in flapping flight. Observe here the motion of the outer wings, which are here the propellers of these animals. The inner part is used for lift mainly, the outer part for propulsion. One thing also is important to observe, that they don't use their tail while flying. This picture is a hawk in flapping flight. You see very well the rotational motion of the outer wing. Now comes one of the masters of flight, the man-of-war bird, which mainly is a soarer and uses the flapping flight only quite temporarily. But you see the twist of the wing while he beats down very well in this picture. This is a spoonbill, which shows us again the motion of the outer wings very distinctively. But these are not all the secrets of the flight of the animals. And you often think, why isn't there a way for us to learn more about this elegant and most fascinating method of flight as it's done in nature? You might think that we don't need it anymore, but we still can learn many things when we translate our knowledge from the observation of nature into the technical application as man has to do it. Everybody of us is thinking about such things if he sees a bird flying around his house, if he is out on the shore and the gulls are flying around his ship. And as the poet said, in the heart of every man will feelings surge above him and beyond, when high up lost in lofty blue space, the skylark sings her glorious song. When over steep and jagged heights, with wings outspread, the eagle soars, and over prairies, over lakes, the heron flies to distant shore. Goodbye and auf Wiedersehen. When in October 1947, Major Jaeger, with the experimental rocket plane, the Bell X-1, took for the first time the speed barrier, a new era of flight was born. The flight in the range beyond the speed of sound. This is a picture of this aircraft, which is the first supersonic aircraft ever built. Now, you might ask the question, what has the speed of sound to do with flight? And why have the scientists all the time talk about the speed barrier of the speed of sound. Well, as you know, the speed of sound is roughly 770 miles per hour. And if I here make a small disturbance, a noise, I make lots of noise, but I clap the hands here like this, then this sound travels away with a speed of 1100 feet per second. And if somebody, for instance, stands away 13 miles, he would hear that clapping just 1 minute after it happened. Now, what is sound? Sound is the pressure, the pressure waves which are created by such disturbance. And the speed of sound is the propagation speed of such pressure waves which go through the air. That means, well, since it is the speed of pressure propagation, and since our aircraft are supported by pressure fields, this speed is also the propagation speed of the pressure field around an aircraft. Now, let's imagine this. Let's imagine there is an aircraft flying a straight course just horizontally ahead. And as you know, it's supported by pressure underneath the wings, suction above the wings, and all this other thing around fuselage and so on. Now, if you imagine just a little tiny particle of air which is ahead of this aircraft. While this aircraft comes along, its pressure field is propagated, and this little particle gets a tiny signal that there is coming Captain Smith with a big airliner, and the little particle, well, polite as air now is, begins a motion to get fine and smooth over Captain Smith's airliner. Well, that's all right, as long as this airliner flies below the speed of sound, below the speed of the propagation of its pressure field. But if now Captain Smith comes with a slick supersonic airliner, well, then this little particle doesn't get any signal before the airliner is there. And suddenly there is Captain Smith and the airliner and the little particle. What happens? A collision happens. And well, it's not very serious because air is not a solid matter, and it is compressible, a compressible gas. And due to this coming together, the air is compressed through a shock wave, and all the particles which are now hit by the wave of the airplane will get a sudden compression shock and a sudden deflection. Therefore, in the subsonic range, the flow field is uniform all over. And in the supersonic range, we have a complete difference. Now, let's go to these charts, which might explain the thing a little bit more clear. You see, here is Captain Smith in the subsonic range, and the pressure waves which are created by small disturbances go out all over because they run out the speed of the airplane. They are far ahead of him, and the farther he flies, the farther ahead are these pressure waves. But if we think now of a supersonic speed of the airplane, then these waves which go out in circles would not reach any space which is on the sides or ahead of the airplane outside of this cone, which is formed by the pressure waves which are exerted from this airplane flying at supersonic speeds. And there is a very distinct cone formed in which only the air can be under the influence of the pressure field around this airplane. Now we call this cone angle, this cone, the Mach cone, and we call the ratio of the speed of sound with respect to the speed of the aircraft, we call it the Mach number. So that if somebody flies, for instance, with a Mach number of 2, that means that he flies 2 times the speed of sound. That would be roughly 1,500 miles per hour. Now there is another very interesting and significant difference between the subsonic and the supersonic flow. When you think, well, you want to make high speed through a nozzle, then you might have a big tank and pump it up and then have a little nozzle and let the air out. And the more you pressurize the air in this vessel, the higher the speed will be. Yeah, up to a certain point. You will find out that you pump it up as much as you want and you don't get out of this opening more than the speed of sound. Therefore, we have to devise a new type of a nozzle. The first man to design such a supersonic nozzle was Pierre de Laval, and therefore we call a nozzle which is now first convergent and then divergent a Laval nozzle. This is necessary because due to this increasing in speed and decreasing in pressure, the density of the air gets lower and lower, and therefore beyond the speed of sound, the density decreases more than the speed increases, and we have to open up. And in the supersonic range, acceleration means a widening of the streamlines, and deceleration to get the streamlines nearer together. In the subsonic range, it's just reversed, as we know, because when we want to make more speed, then the streamlines have to come together nearer by. And diffusion means deceleration. Therefore, all these geometries of the flow fields are completely changed. In the subsonic range, we see that the flow is completely symmetrical. And when we neglect the friction, the forces are in balance. But when we think about the same pump and a supersonic flow over it, then we see at once that we have in front a pressure on the surface and at the rear a suction on the surface, which makes, since this is the pressure force, this is the suction force, which makes a component of the forces in the direction of the flow, a drag component besides of friction drag. This is the wave drag of the supersonic flow, which then necessarily has a strong influence on the efficiency of the supersonic aircraft and diminishes the range and makes it necessary that such aircraft have large power and a large fuel consumption. On the other hand, as we see it here, also the pressure distribution on the wing changes considerably, and we have a shift in the center of pressure, which was here at the first quarter of the airfoil, and here is almost at the center. This makes a stability problem in the supersonic range. But let's look now at some pictures which we have from the flow in supersonic wind tunnels and in nozzles. They are made by the so-called Schlieren method, and what we see is the density changes in such flow. These pictures are made available by the National Advisory Committee for Aeronautics in Langley Field, Virginia. We see a thin airfoil in the transonic range. That means going from the subsonic flow into the supersonic flow range. At the present time, we see what is called buffeting. That means we have a formation of oscillating shock waves on the both surfaces. Finally, these oscillating shock waves come together into one straight shock, which is now beginning to form at the rear part of the wing, and with increasing Mach number. You see it from the finger, which moves down on the scale and which is now in the range of something above 0.9 Mach number. The shock travels backwards towards the trailing edge and finally forms an oblique shock, so that the whole flow on the surface of the wing is supersonic, which you also see from the slim Mach waves which are generated from the surface of the wing. Now we reach the Mach number 1 and the flow is completely supersonic. Another interesting effect can be seen in the jet stream from a rocket or a jet engine in the supersonic range. You see waves forming in such supersonic stream, which is here on the first supersonic aircraft, the Bell X-1. And we see it now here as an experiment in our laboratory, where we have a nozzle on the left-hand side. The jet stream comes out with supersonic speed, and the dots we see are the waves which are formed in this jet stream. The more we go down to the sonic speed, the smaller the wavelength gets, and finally our stream disappears completely when we have subsonic flow in this nozzle. Now, when you think of all these problems which arise from the flight in these high-speed ranges, then you might realize that the original concept of the aircraft as a powered glider is probably not the final solution of the aircraft for the use of human communications. See, in the meantime, while we were working on these high-speed problems, a new type of an aircraft came up. This was a helicopter, which could fly without any speed. And it has taught us a very important lesson, that such a feature to hover and to raise from just a tiny spot on the ground and to come down on it is so important that, well, many other things are not important with respect to difficulty of obtaining such features. So the question is, can we combine this low-speed aircraft with our high-speed aircraft in one new conception? And when you think about it, you come to the conclusion that this certainly might be possible, but that we have to have then an aircraft which is not derived from the natural prototype, but which we conceive from scientific and technical information. A man-made flying machine. Now we have begun with this work, and to distinguish it from the aircraft, the powered glider, which is called the aeroplane because it has planes, we call such types an aerodyne, a body which is dynamically lifted. And this dynamic lift is made by an internal flow system. Now we are just at the beginning of such development. And I can show you here one of the first models which we have developed from this type of an aircraft, so that we might show to people what we mean with this development. You see, this is a small model which is lifted by a row of 4 shrouded propellers. You remember, as I have shown them to you in our propulsion program. So in each of these holes, as you might call them, is an electric motor which drives a little propeller. The stream which comes out and lifts the thing goes over certain control surfaces which are down there. And these are stabilized by a gyro system, and I can also control them from a seat. The electric power comes in through this cable, since we cannot carry batteries in such a thing. And also the control signals which I give from the seat go also through the cable. You see, we have an undercarriage, and when I have good luck, then I can take it off and bring it down. Now this is the seat, and you see I have a normal control like in the pilot seat, and from here I can switch in the power for the gyros, as I do it right now. And then when I switch in the power for the engines, the thing will take off. Now we will try another flight with this model. You know, this model was designed about 4 years ago, and it actually serves the purpose to show that you can stabilize a flying body in the low-speed range. And this was the purpose of this model, and we obtained this purpose by using certain gyroscopic action to control flaps to stabilize the thing in flight. Now, let's try it. Now, the models I have shown to you in flight are just the beginning of something which has to be developed into an efficient aircraft type. To give you a little imagination of what might come of such a development, we have here in the tunnel a model which might illustrate the use of such internal flow systems which give lift and forward thrust and can be used in the flight at no speed as well as in the supersonic speed range. We come now to the end of our program. And I want to thank all of you who have watched The Secret of Flight go on the air. I want to thank also the Office of Naval Research and the Collins Radio Company, who have given the permission that we could use this smoke tunnel and some other equipment. We have tried to give you a short glimpse into the wild field of aeronautics. And we hope that we have raised your interest on several problems in the field of aviation. Our time was certainly short, and we couldn't show you many things we would like to. But nevertheless, the few examples we could demonstrate were, as I hope, of a more general interest and gave you the idea of what might come out of this development in the future. See, the work of the scientist and of the engineer in this field is certainly not an easy task. And it is necessary for the evolution of new principles and of new knowledge that this is carried on from one generation to the next. Despite of the tremendous progress which has been made in these first 50 years of aviation, many problems still await their solution, and every day opens up new fields, new views, new aspects in this new science. As you know, today, aviation serves mainly and to a large part as a defense of our freedom and as a deterrent of war. But besides of it, aviation has flung his arms around the world to bring men to men and to create mutual understanding and new friendships. You see, to break the speed barrier was a scientific and technical problem. But this may serve at last to solve a great human problem, to break the barrier of fear and distrust, and to bring love and happiness to all men. Thank you and goodbye.